go on seeing as. So, are there any questions based on? Nope, no questions whatsoever. Again, that makes me very worried that it was so unclear that you can't even actually ask a question. We have been jumping around a lot, but and again, part of what I'm trying to do is actually tell you things that are gotchas or a little bit beyond what you'll see in other introductory documents or whatever that are fundamentals. Just to get you aware of them to some extent. I finally drew this. I finally actually took the time to draw this diagram. This is the call stack. Okay, so remember, this is what we were talking about the first day and the second day too. This is the call stack where we call this. So this scatter.smooth calls XY coordinates, so you see things going down this way, but the searching is done along this dimension once we're in each of those functions. And one of the things you can actually try to do is, instead of, if I don't call scatter.smooth, but if I define a function in my own workspace, in my own global environment, which we'll talk about in a moment, what happens then? How do things differ? It's exactly the same rules, but, hang on a second, it's exactly the same rules. How do I mute this silly thing? Yeah, it's exactly the same rules, but different environments. And that's, if it matters, and hopefully this never matters, it just works for you and you're all very happy. For those of you who use things like dplyr and the piping operator and some of the other packages in the tidyverse, sometimes it doesn't work the way you think it does, and then it can become incredibly cryptic. That's because it's using non-standard evaluation. So sometimes it's very important to actually understand this stuff. Okay, so I put that on the web page for the workshops. So no questions. No. One of the things, I'm not sure, I don't think I put up the files yet for today, but here Nistara asked me a question at the end after last session on Tuesday, and look what Pamela did. Finally, we have a whiteboard here as opposed to the ones where, okay, anyone over there can't see a thing. So this is perfect. Okay, so one of the things we were talking about was this, and again, hopefully you don't see matrices. We'll see them in a moment where they come up because of the call to sapply, collapsing the result into a matrix. But oftentimes you don't see matrices, but if you do, and they can be very useful for certain computations, but we have a matrix here, and I was basically saying you can subset by, if you combine two columns, if you get two columns here and k values here, where this is ij, this you can actually subset into this matrix using a two-column matrix, which is very powerful. And you can also then have another one. So this is sort of, these are the ij pairs, and this one here is a logical matrix, which has exactly the same shape as this one. The dimensions have to be the same, and then you can subset by here and get the trues and falses out. And Nistara asked me, what happens if I actually have this, if I have a true and false here, how do I get these guys back? Many times you don't care, actually, because if you just subset straight in, you get the results back, and who cares? But the way you do this, remember, we actually introduced, I showed you about this function called row. So let's call this M. So this is a matrix. Okay, of random numbers. I'll pop up the example. Okay, just random normal values. So this is numbers. So now if we take a look at something like the following, which we say, okay, let's define A to be equal to M is greater than 0. So basically, this is a matrix. This is a vectorized operation, but because this is a matrix, R will leave the result as a matrix. Okay. Which is actually kind of in general, this doesn't always apply, but basically what's going to happen is it's going to treat this as a big long vector, because all matrices are big long vectors. They just happen to have this extra attribute called a dimension. So then what we'll end up with a bunch of logical values over here, exactly the same length, because it's a vectorized element-wise operator. And what will often happen in R is the attributes of this, all of the attributes of M will become the attributes over here too. So the names will remain the same. The column names, the row names will just get transferred over here. Sometimes we drop all of the attributes for intentionally, but in many cases we just actually carry this across. And one of the dimensions, one of the attributes is this thing called dim. So then the dim comes over here too, because we just inherit all the attributes, and now we still now it becomes a matrix again. And that's a general principle, is that there's nothing magical going on. Oh, R knows about matrices, so therefore it makes this one a matrix since it happened over here. It's just that all the attributes get passed across, and as a result it inherits those, and hence, because it has a dimension attribute, it is a matrix. So this is good. So anyway, let's call A to be just this big logical vector. That's just here, truths and falses. So one of the ways to get this guy is, hopefully, give me the rows of A. Okay, so that gives me back, so let's think about what's the row of A? It's just equal to 1, 1, 1, 1, 2, 2, 2, 2. It's the world's most boring matrix, okay? But it's very useful. So now the row of A is that guy. So row of A, square bracket A, is actually this column here. The ice. These are the rows corresponding to all of the elements in M which are greater than 0. Does this make sense? It's early in the morning to crank this up. Okay, this is the sort of logic that we use an awful lot of. It's so much easier when you're in another language where you're doing vectorized, where you do element-wise operation, where you have a for loop and you loop over and then you get the corresponding entry or whatever. Here we're kind of doing everything in bulk, and it's a little cryptic until then you go, oh my God, I get it. And now it's really succinct. Cryptic and succinct, okay? Just one line, okay, we're getting, because this is rows, okay, blah, blah, blah. This is a matrix. Now, when I subset it by the logical matrix, I get only the values for which this is true, which will give me back what? It'll give me back the row numbers corresponding to each true value here. Is that true? Is that clear? Because I said you could subset a matrix by this, we can subset this row matrix by this. Okay, and this is A is great. This is M is greater than 0. This is a matrix. This is the matrix I'm talking about. So row of A subsetted by a matrix. This is a matrix. This is a matrix. We pull out only the true values, which gives me the row numbers corresponding to the true values. And then if I do the following, if I do col of A, square bracket A, that gives me, well, now the column numbers are 1, 1, 1, 1, 2, 2, 2, 2, 3, 3, 3. Now when I subset the truths of that, it gives me the second column over here. Happy? So this is an example of, we're actually illustrating how to, we don't need this, but it's a way of actually utilizing the row and the column functions to actually go and get some computations. It's pulling out the elements that we actually want. This is where subsetting by a logical matrix is extremely powerful. Okay, if you just try this again, or if this is cryptic and not comprehensible, okay, that's perfectly fine. Just try it one line at a time and actually see what's going on. You go, oh yeah, that makes sense, and change the dimensions of the matrix and change the matrix and see what you actually get. You'll also notice this. When you're trying to debug stuff and try to understand it, and you're using random numbers, which is handy, set the seed so that you don't get different random numbers each time. And as a result, you don't know what's changing, the random numbers or the computations that you're doing. Okay, so this is answering the Star's question, but I thought it was relevant to everybody. It's just we're subsetting this matrix, okay, which we get this matrix. We subset it by the row here, by this logical, the column by this logical. This isn't n col or n row. This is actually that bizarre matrix that you would think we would never have any need for, but we do, which is how to get the rows and columns for a particular matrix. Okay, so that's two-dimensional subsetting for matrices. A lot of people don't seem to know about this, so that when you are using matrices, this is remarkably helpful. Okay, and again, it's very succinct once you get it.
Is this a good way to do it, even when M is very sparse?
Ideally, ideally, if you use a sparse representation, it should still support the same subsetting. It's just that the implementation should completely change underneath. So if you have a very sparse matrix, so by sparse matrix, we're basically saying there's an enormous number of zeros in them. So therefore, really, the simplest way to represent them is just to mean a good way of representing a very sparse matrix is by saying in position I1, J1, so some numbers, okay, so 2 and 7, okay, we have the value 2.6, okay, and so let's actually make this explicit. So this is in position 2 and 7, here's the value, and in position 107 and 2009, we have the value 3.7, and that's it. Okay, we've got a matrix that is let's just say it's a 200 by 2010 to be okay, and so this is a big matrix, not really, but it's a big enough matrix, but it's only got 2 values that aren't 0. You're way better off just representing it as this. So what you'll see today, I'll illustrate a little bit, not in this particular case. There's a package called the matrix package that comes with R, and you can actually represent sparse matrices in this way. But you should be able to say something like, whatever the function is, here's a sparse matrix, here's the data, here's M, and you should still be able to say M is greater than 0. And now that may or may not construct an actual matrix, or it may return a sparse matrix. Okay, but then when you do M square, when you do this, when you say A is equal to this, and you say A square bracket. Well, when you do call of A square bracket A, okay, in theory, and I'll explain this later on, in theory, the people who wrote the sparse matrix package could actually define what this is, okay, to be different. So it would not return a full matrix of ones, but it would actually just be sparse. Or they could just leave it as this, but that could be very big. Okay, in this case, there's no sparsity here, but they could represent the fact that, hang on a second, the calls are very simply, it's just repeated. But they can also redefine what the square bracket is for a different for a sparse matrix, in which case all of this, they could hide all of these details. Whether they went that far is another matter, whether it's actually, but if you need to, you can actually also do the same thing. But in theory, we would really like all the same logic, all the same syntax to work identically, but hide all the details. Okay. So that was those things, and this C bind that I sent. I didn't actually bind them together. The C bind actually again takes a column, takes another column, and then combines the 2 columns together. Will potentially it's different from C, which would just actually unravel them all together. Huge, very long vector. But we actually want to treat this as a something by 2. Come on in. There's a place somewhere. There's one here if you'd like one. This is where you were almost last time. Okay. So Nastara also asked me, which illustrates that everyone should have asked me. I started talking about somebody asked me, how would you represent the data from a simulation? And I said, it depends on what you're going to do with it. And then I said, hey, here's the way I would think about doing it, which is to stack everything on top of itself in the data frame. So let's just take a quick look at this. Okay? I actually wrote this. I just wrote an example. Okay, and this, one of the things I want you to look, when you're looking at this, we'll just walk through this reasonably quickly. What I want you to think about is, what's wrong with this? What can you do to improve it? There's nothing really wrong with it, except for one little thing, which I injected for fun. And there's a couple of other things which we could do better. So I just want you to think about them, some of which we've spoken about. This is the bit where, this is your thesis, okay? Where you spend years developing this simulation function that goes off and simulates absolutely everything. This is where I go, we'll take that as read. So but I have to have something, so all it does is generate a data frame with 2 columns. And I kind of try to make the 2 things. Originally, I just made two random sets of numbers. Then I tried to make them correlated in some way to make them slightly more fun. Okay. So this simulation takes in a mean and a rate for an exponential distribution. Okay. It actually figures out how many observations by generating another random number, which is related to A and B. Okay, so the actual number of observations I will get back changes for each simulation. Okay, I create X from a random number, from a random normal with this mean. Then I create a data frame with that column, and then I make Y be somewhat correlated to it. So it's X times the random exponential, where then I sort of start screwing around with all this stuff. I have to put in the min here because somehow this could be negative, in which case the exponential rate being negative would be probably an error, maybe just not a number. Who knows? We can debug this and see. Okay, so I threw this function together. This is where you put in all your hard parts, but this is going to do the simulation, and I'm just going to declare it's going to return a data frame. Here this was the original question, like what we have different conditions that we start with. Okay, so we simplified it, and again, this is what I do, is I just try to come up with the simplest example that illustrates what we want, and then see where it all falls apart. And we debug from there. You always break things down into nice simple examples and then grow. So this is the first condition. It's got two levels, two A and B, okay, on and off or whatever it is. And then we got a second condition, which is high, medium, and low. And then basically when we were mapping this, I need some numbers essentially to go with these. We're going to generate random numbers from it. So I just, again, this is highly contextual as to what you'd be doing. So I just said, okay, let's say mu is equal to these two guys. So connect the A here to 10, B to 20. This is going to be A and B. This is going to be the two values of A. The rate for the exponential is going to be these three, again, connecting it to here. And what I said was that we're going to actually do several replications for each combination of these two things. Okay, so for A and high, I'll do 10 replications. For A and medium, and I'll do 10 replications, and so forth. Okay, life is good. Oftentimes we may actually change the number of replicates. This is often a very good thing, because if that number changes to be huge, for some of them we can only afford to do 2 replicates, whereas for small numbers we would do a lot of replicates. Whatever, that's fine. Okay, and so this was the piece of magic that helps a lot. This is, remember we had these for loops, and it's like, when we get 10 of these conditions, I'm going to have so many for loops. I'm going to actually run out of letters. I'll start with I, and then I'll go to J, and then I'll go to K, and then I'll go, dang. I'm going to start getting very ugly. So expand.grid, it will eat up a lot more memory. But if we actually run this, let's go over to here. What was it? So let's go like here. Do this. I'll cut and paste this in. So hello. I do need that, don't I? Okay. So this is G. So this gives me all possible combinations of these guys. So, and again, these aren't factors. These are actually these are character vectors up here. Now they're factors. Down in here, I didn't tell it not to use factors. So we talked about factors, but they probably make sense. You can actually tell they're factors. How? No quotes. Okay, again, helpful. This is a useful thing to. I was reading something that somebody was writing. They said, you really want to focus all your attention on programming. So if you have any difficulty with typing, you should overcome that soon. And the way they were suggesting is to get a T-shirt and put it over your hand so you can't see the keyboard, and just practice and get used to doing this so that you don't have to think. And likewise, when you look at this, it's like, there's no quotes, it's a factor. Bingo. Just that hopefully that's a lot of experience, but it is very helpful to be able to visually identify what the types are. Likewise if you remember with the factors having a less than NA greater than, and that indicates it's an NA, whereas if it's just NA in a factor, that's the actual level. So this is what we actually get. If I put in expand.grid and I had multiple conditions here, this would just go and actually construct. For as many conditions as I put in, it would have that many columns, but it would actually then generate every single possible combination of values. Which is very similar, by the way, to what happens when you type table of 2 factors, or 3 factors, or 4 factors. It generates a multi-way table, okay, of all possible combinations. But what table does is count how many there are in each group, or in each combination. Okay, so that's fine. So now we've got this, and now we run down. So here's the Here's the bit that does all the simulations. Okay, why are we doing this? Okay, so what are we doing? We do an lapply. We're going to loop over every single row of this. Okay, this is a data frame. It's kind of weird. We could turn it into a matrix if we wanted and use apply. That might be fine. Okay, remember, apply will turn it into a matrix. The reason I didn't do that was because these may be a factor of A and B, but these may be actual numbers, in which case then they'll all get turned into character vectors. Okay, so let's keep them around as a data frame. But if you don't need that, you don't need it. So you've gone too much work. But we'll loop over. This is kind of one of these annoying things. We'll loop over 1 through the number of rows of G, and then we'll go in and grab the row of G. So it's hard to loop over the rows of a data frame without corrupting them, without converting them into a matrix. Okay, so I get my settings. So this is going to be A and low here. Okay, and now I just repeat. There's a function called replicate, which is like a loop, except for it does the same thing over and over again. And it says, okay, go grab the settings, go grab the first one, the A, and then go grab the low or high. And then index, because now these are character vectors. So now index back up to mu. Okay, simplify, don't simplify, please. These are going to be data frames all coming back. sapply, if we used sapply, it might say, oh, look, they've all got the same length. Oh, look, I'm just going to make them one big long vector or something. So let's not do that. We're going to force the issue here. So this should come back with 6. There's 6 rows. I should get 6 elements back. This thing should come back with a list with 10 elements, because I didn't simplify, and each element should be the result of sim, which you, of course, remember as being a data frame with X and Y, with how many rows? Rows? 2 columns. How many rows? Depends on the random number that I generate based on the default argument for the, because I only pass in 2 settings, okay? You would change your sim here to be your own function name, and life is fine. We run this. Oh, get an error, okay? That's because we haven't actually defined sim, because I haven't sourced this in. Okay, so that's an example of debugging. Okay, that was easy. Notice, by the way, most people won't have this. We're going to talk about this soon. Most people won't get this coming back. They'll just get an error that says, could not find function sim. Have a nice day. Okay? And you'll get the prompt back. I always, for better or for worse, I always get this. No matter when I get an error, I get this stack, this call stack that says, this is what you started with. This is then what happened afterwards. lapply calls your function, which was this guy here, the one I defined, which then called replicate, which then called sapply, because replicate just uses sapply. And the sapply just calls lapply, we know that. And lapply calls another, hang on a second, are we going around in circles here? No, because these are different funs. This is one call to lapply. Fun is a parameter in that call frame, so we can go take a look at this, and we will, okay? And this is a different fun because it's a different call to lapply, so we can actually look around. This tells me the entire call stack, like the one that we saw with scatter.smooth calling xy.coords and so forth. But what I'm able to do here, when we'll talk about debugging, is I'm able to go back in and walk into, I'm able to look and see the call stack, and I'm able to jump into any one of them and examine what's going on. I can see all the variables, all the parameters, and I can see what values they have, and I can change them if I so desire, and then continue on. Okay, so this is a very powerful mechanism to actually be able to debug what's going on, or just explore.
And the third one, what is this like comment for?
That's, okay, this is in line number 4. That's line number 4 of the function 1, 2, 3. So there's a 3, but there's a 4th element, so it's 1, 2, 3. So we're kind of, that's basically what's going on. Okay, it tells us a little bit about where it comes from. Sometimes you'll get line numbers of files in here.
Okay, so just telling you that that's where the function is. It's not just, that's not like because it's red, it's an error or something.
No, this is I live in a weird world. No, this is because it's a comment character. It actually, my text editor then treats the whole line as a comment character. No, thank you. It does not tell me where I am. This is, each of these is telling me where I am in the overall function in which it's being evaluated. Okay. So this is very useful. I'll tell you how to make it do this all the time if you want, but even afterwards we can always get back to what we wanted. Let me go back. Now we're on. So the nice thing about this is very fast. So here's what we actually get back. And again, this is one of the things I'm encouraging you to do always. Okay, and as I told you that I do this, and I genuinely do. When I was writing this, I knew what I wanted. You have a plan. Sometimes the computer doesn't quite agree with you as to the details, so you check every single step of the way. I do this. Let's check the class of ants. Okay, it's a list. Let's check the length of ants. What should the length be? 6. You should know what the length you anticipate is, and then verify. Okay, fortunately enough it is. What are the names of this? Okay, there are no names. It would be very useful for me to put names on this so I knew exactly where they came from. So I could, so we're just looping over 1 through n rows, so it doesn't really know. These are integer values, they don't come with names. We might want to do something like the following, which is paste of G1 and G2 with sep equals, let's put in a dot. If we do that, we could put these as the names on ants. This would be a good thing to actually remind us where they came from. Okay, don't have to, but it really does help. Otherwise, the six come in whatever order, especially when this gets more complicated. That's fine. So we know what this is. So let's just do the following. Let's go through the ants, the class of each element. We asked what the class of ants was, but not what the class of each element was. Okay, that's fine. They're all lists. Okay, well, we can do the same thing. Now let's go through and actually find out what the length of each is. They're all 10 because I have 10 replicates. Okay, this is good. This is not a surprise. This is not debugging. This is verifying. Okay, and honestly, I do it all the time. Every time I do a computation, I check because there is no point in going on any further if this came back in any way odd. So remember, so let's just take a look at ants of 1. Well, actually, let's just look at the first one. Okay, I like to do this. What's another way of doing this? So here's where I could use ants of double square bracket C parenthesis 1 comma 1. So they go get the first element and then go get the first element of this. And I've never found a good use for that. Okay, so so this gives me that there. So this one has 45. So let's actually just do the following. Let's just do sapply over number 1. And actually, we know that these are all data. We know that these are all data frames. I do. Okay, we haven't actually checked that. Well, let's just check it. Okay, so this is over just first element. Okay, they're all data frames. What could possibly have gone wrong in 2, 3, 4, 5, 6? Nothing. It's the same code. Yeah, right. Okay, so we should check all of this stuff. There's lots of ways we could do that. What I might do is I might actually unlist them. Okay, there's an unlist function, which we'll see in a second. And unlisting them would actually then, I have 6 elements in my list. So if I unlist those 6 elements, I would get back, well, each of those has got 10 elements, so I should get back 60 elements. But unfortunately, unlist is a little aggressive, and it will then unlist the ones underneath that as well, which are the data frames. So I will then end up with 60 times 2 columns, and then actually, hey, they can make those into vectors. I'll just make one massive long vector of numeric values, which is exactly what I don't want. But fortunately, I can say unlist, do it 1 level, please, and stop. That's the recursive equals true or false. Okay, so I can basically say, don't do what you think you're going to do. But that would make it easier to ask, are they all data frames? But we don't need that. Let's just check the number of rows in each of these. Okay, there we go. So we are seeing that there's a different number of rows in each of these things. Okay. So what's our next task? That's kind of useless to me because what I want to do is I want to draw a plot. How do you know what I want to do? It's your simulation. I didn't. Okay. So this is where it really does depend on how do we store the data? How do we arrange the data? It depends on what we're going to do with it most commonly. And sometimes we're going to do 2 things with it where we need it in different formats, a different structure, but we'll get there. We have to pick a default one. We could leave it like this if we want. This is maximally annoying to do any computations on it, but I want to draw a plot where I want to draw X against Y against all possible combinations of condition 1 against condition 2, and I want to see, are they the same? Or is there are the means changing? Are the correlations changing? I don't know. I just want to actually look at this. So again, we go through all this. So here's one of the things we can actually do. Let's unlist. the 6 elements that's on list them. Okay, so and again, this is tricky. Let's actually look and see what we have. A picture is useful. Okay, so we've got 6 elements. This is really helpful to actually say this is ants, because I'm going to call ants 1 something else. Give them good names. These are not good names. But this thing here is what? It's a list with 10 things in it. Okay, there's now 10 here. And same with over here. There's 10 things in here, 10 things in each of these. And each of these 10 things is what? It's a data frame with 2 columns and some variable number of rows. What do we want to get at for this? Okay, so when we unlist, what I want is, and we can do this in so many different ways. You've got to pick whatever one you're happy with. I want 60 data frames. Okay, if I get 60 data frames, and here's the strategy we're going for, just to be clear. And by the way, what we're doing here is everything we talked about in the last 3 days, we're using. Okay, S-apply, L-apply, blah, blah, okay, subsetting, so forth. So I got 60 data frames. So if I unlist that with recursive equals false, it will stop. It will not go down into the data frames and unlist those, as I said it might. So we'll stop it doing that. So now I get 60 data frames. So I have a data frame, which is this long. I got another data frame, which is this long. Okay, each of them has 2 columns. Another one which is smaller, another one which is longer because they have variable number of rows. There's 10 data frames here, all connected with A and high. Yes? This is condition 1 versus condition 2, the first one. Then I get another 10 data frames with condition A and medium. Okay, then with A and low. And, you know, this is what's going to happen, Pamela. I'm going to start writing on the wall. So we go through all 6 of these. What I want, and this is a very common way of representing this, is I don't want these data frames. They're not much use to me. If I pass them to a plotting function one at a time, there's a lot of work for me to do. What I actually want is this. X and Y, and I want 60 data frames stacked on top of each other here. Okay, they have different numbers of rows, so that's fine. And then what I want is I want condition 1 here, and I want condition 2 here. Okay, and I want this to be A, all the way down to the top 10. Okay, for the first 10, actually for the first 30. Okay, but this one will be high, high, high. Then it'll be medium, 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 medium. Okay, and actually, by the way, what I'm also going to do is I'm going to put on the simulation number. Okay, so this will be 1, 1, 1, 1. Okay, and then it'll be 2, 2, 2, 2, 2, and then when we get past down here, we'll go down back to 1, 1, 1, 1. This is the replicate number within each group. Everyone happy? That's the goal. Everyone know how to do this? Okay, so it's not very hard. Okay, here's what we're going to do. But we do this all the time, and if you're using something like debug or something like that, or you know, this melting and casting are related to this. But I think it's helpful to actually know how to do it yourself because it's so simple, but it also reinforces an awful lot of really what are you actually trying to do. So what we've done, this unlist business, and again, you notice what I'm doing here? I check every single step of the way that I have not managed to completely corrupt everything I'm doing and go on and make my life complicated. What we're basically doing is this gets the list of 60 data frames where we stop. And now I want to stack them all on top of each other to get this guy here. We'll take care of adding these guys on later on. But I want to get this thing all stacked on top of each other. And as I mentioned before, we could actually just type in our bind of temp1, comma temp2, comma temp3, comma, oh my God, you know, thank God we've only got 60 possible data frames. But here, I basically got all the arguments in a list. And I want to pass them all as multiple arguments. So I don't want it to say, I don't want rbind to see one list with 60 elements. I want rbind to see 60 elements as separate arguments. And do.call allows me to do that. It says, hey, call rbind as if each element in the second argument is a separate argument to rbind. So ants1 is now my big data frame. Let's actually just again. You can. Why don't we actually check this? There's the length of this guy. Let's just check we got. 60 data frames in my temp. That's good. Life is good. Now let's stack them all on top of each other. Okay. By the way, why do I call it ants1 and not ants? I already have ants. That's no problem. I want to get rid of ants. So I'm actually sucking up more memory here because I've still got ants. I'm going to have to remove it if this is huge. But regardless, why do I call it ants1? This is a sociological thing, or this is not a technical issue. It's a very practical issue. It's because I'm going to make a mistake, okay? And if I've overwritten ants, it's gone, and I'm going to have to run ants again. And if that took me 6 hours to run or whatever it is, I'm screwed, okay? So if I really care about memory and all that sort of stuff, and I need to get rid of temp or ants, I'll make it, and I'll save it to disk. But I want to lock it down because this can be very expensive to reproduce, and a simple typo can just wipe it out. Okay, so let's be cautious. Ants1. So now we've got that. So what do we do this? Fortunately, it's very fast. What's the class of ants1 again? It's a data frame. What's the dimension of it? Okay, it's 2,815 with 2 columns. Okay, the key thing for me is 2 columns. What I possibly might want to do, though, I might want to do the next line, okay, which is, I'm pretty confident, but let's do this. So let's go back to my answer. I actually really need answer. In this case, it wasn't just caution. I need extra information, which I could have computed ahead of time, but I need to find out how many. I need to find out how many rows there were in each of these 60 data frames, because that's how many times I'm going to replicate the A, okay, and then the B and the C, there's no C, then the high and the medium and low. I need to know how many times to replicate these guys, okay, and they're going to replicate in different ways. The A's go down the whole time, and then we switch to B, whereas the high, medium, low change more rapidly, okay. So when I do this basically tells me the number of observations in each of the 60 things. So sapply, so here I'm doing 2 sapplies. Sapply over the list of 6 items. Then on each of those, loop over all 10 items in that and get the number of rows and then add them together. Okay, because I want the total number of rows. And so hopefully, if I say what's the sum of n, that should be
2,000.
It better be the same as that or I'm in trouble, okay? Okay, so I just checked. These are, I mean, this is the, I'm trying to show you this, this is actually the way I think when I'm doing stuff. And I say, I kind of do know what I'm doing, and yet I still am incredibly cautious, because you just need to validate every single step of the way. This is very different as I mentioned in, I think, last Thursday. There's 2 modes you're in. You're interactively using R to do things, but we're actually writing software, but we're doing it line at a time. So it's kind of weird. When I go into production, when I turn this code, okay, which we do, when I turn that code into a function so I can reuse it, I'll take away all the checks because I've validated that they're there. Now I'll throw in some data or some inputs that will actually cause it to have an error, and then I'll debug and I'll have to bring those checks back again. But I won't put them into a function, but I do them when I'm incrementally just developing what I'm trying to do. So this is the next step that we actually will do is the following. I'm going to repeat the A and B, the condition 1. This is condition 1 status. I'm going to repeat it how many times? Basically n times. Okay, this is a vector. N is a vector, so it will actually do. So what will it actually do here? So we have to check that this is correct. This is where life gets really messy. So this is okay. So there's G1. Here's N. So what will that do? What will rep of this guy do? So we basically want to get a bunch of A's. We want to get a bunch of B's. We want to get a bunch of A's. We want to get a bunch of B's. So it's a good idea to do this following sort of thing, which is, well, we can actually, so let's just rep con1, and let's put in 5, 6, 4, and 3, and 4. Okay, I'm taking the first digit basically out of these, but rounding them up just because I want to see if this is giving me what I expect it to do. This is where you can go wrong very easily. Okay, if I could just type. How many? Count one. I'm missing one. Type 3, 5, 6. So put in the 5. I'll put in the 5 here. Okay. How many do I have here? That's 2, isn't it? Column 1 is 2. So how is this working? So we've got this. So I actually want, I need to do G of 1. Okay, so we'll do this. And that's what I get. So I get a bunch of A's. I get 5 A's, then the 6 B's, then 4 A's, then 3 B's, and so forth. So is that what I want? Okay, just check if that's what I actually want to do here. Okay. So we have to patch this up. But basically, rep is going to be my friend, which is going to basically repeat this the right number of times. When I get down to here, I may have to do something else because I may have to do them in different order. Okay, because then I need high, medium, and low. So we're going to actually have to go through and check that this one works. Okay, but basically this is I'm going to make this to be 2,815 elements long with the correct A's and B's in here. We'll just use rep to do this in the right replication order. And we put it into our new data frame, and that gives me the 3rd column over there. We get the 4th column over there by doing something like this. Ignore this and this. It's just another call to rep. We may need each in here or whatever it is. We have to come up with the right magic. But here's what I wanted to do. High, medium, and low are actually ordered. Okay, and high, medium, and low turns out to be if we put them in here, they'll be alphabetized to be the wrong order. Okay, whereas I actually want high to be the biggest one, medium, and then low. So I'm going to make this a factor, but it's more than a factor. It's an ordered factor, and we talked about this on Tuesday. So let me just make it an ordered factor. Okay, and I basically say here are the values. Oh, and by the way, I am going to tell you what the levels are. Okay. And I'm going to tell you that they are, you're not going to use them, you're not going to use the alphabetic sorting of them. I'm going to tell you which ones are what the order is. So I'm going to actually say, I had them, for some reason I had them as high, medium, and low. So I'm going to reverse that order, and life is good. And now off we go. Okay, and then for the sim number, the simulation number, we'll go off and we'll figure out how many there were. We'll go off and we'll generate values 111, 222, 333, up to 10, and then start again 111. So life is good. By the way, how many of you have seen this function? Okay, the name gives it away. Okay, there's a function in R called stop, which just comes to an abrupt error. Okay, and says there's something wrong, and you print an error message. This one just says stop if this condition is not true. So we test this condition, and I want Q1 and equal to Q3, which are, what I'm basically doing is I'm going to go and compute the simulation number, which is this, and then I'm going to do some computation on it to make sure that it actually agrees with the number in each, and life is fine. Okay? So I go off and I do these computations, and you can take a look at these. You can dig through these and figure things out. Ultimately, at the end, what we're going to do is we're going to draw a little plot, and this is why I wanted it. I want to draw Y against X in my big data frame, but I want to actually have a panel for each combination of condition 1 and condition 2. Okay? And that's the way we set this up. Everyone happy? Anyone see? Yes. You're not happy.
The ordering of the expand grid versus the label or the ordered factor.
Yeah. It's not right.
That's not necessarily accurate.
Well, it isn't. It isn't. I like your not necessarily accurate. It's not accurate. It's not correct. Why isn't it correct?
Because should we reverse 70, 72 versus 2? It's not good.
Well, I haven't talked too much about it. Nistara pointed this out, and I knew about it. Okay, there's a couple of things wrong with this. But I threw it out, actually. When I said this, I actually said something to tell you what the answer was. Okay, or another thing you can try. I said I'm going to tell you what the levels are. Did I? I tell you what the labels are. Okay, which is different. Because if you take a look at the definition of ordered, okay, it's this. Well, okay, that's a very boring function. It just basically hands straight back to factor. Okay, so here's the definition of factor. Okay, now it helps to understand. Here's this, I expect a character vector. There's no default value for levels, but it comes out of these guys. But if you give me the labels, then that's what I'll use for the levels. this is the labels on the level set, okay? But if you don't give it to, I'll actually compute them off the level. But I gave it the labels, and I didn't give it the levels, and then everything goes to, now I'm actually labeling things in the wrong order. That's one problem that actually, that is one reason why it didn't work. There's other things where we actually have to make sure we get them all to match up correctly, that we repeat them in the right number of times. But this is a simple one where we actually, I should have said levels equals, and I think that will behave itself correctly. So you have to understand the difference between the levels and the labels and how they interact with actually the observed values. So this is fun. And that is just, to me, that's so easy. We'll start with L, the labels and levels. What is the connection between the two? It's important.
Can paraphrase what the difference between a label and a level?
I have something written down in one of the notes that I'll pop up later on. I didn't get a chance, but let's just do the following, which is C of A and B and C. Okay, so let's call that Z. Okay, and now we do something like factor of Z. Okay, that's fine. So let's just take a look at the levels on this guy. Okay, now let's just see what we're doing here. Now let's do this where we do that the levels is equal to C, B, and A. What do we get? We get two A's, a B, and a C, but the order is CBA, whereas the order here was ABC. Happy? So now let's just go move one along and do labels. Okay, now we got two C's. Bad news. We've just mislabeled. Okay, it's just we've still got two values corresponding to the first level. And everything else is, correspondingly correct, but we put the wrong label on them. Whereas here, when we said these are the levels, we got two A's, and here we got the B and the C, and the levels, we modified the order of the levels. Clear? No? So one is a labeling issue. What we're translating the names. And okay, I mean, I can put in if I wanted to. If we want to really go down over here, X, Y, and Z here. Okay, and now we sort of end up with this thing. So I'm changing. I can change everything around and what they actually represent, but I can specify both the levels and the labels, and now I can get myself into all sorts of interesting brain twists. Okay, but in my case, this is misrepresenting the values that I come back with, because I'm saying, oh, by the way, change A to C, and change B to B, and change A to C, which is very different from actually, no, these are the levels that I want you to represent. Okay.
So this labeling is actually a transforming function.
It's a transformative functioning, but a function after we've essentially set up the levels. Yeah, we're kind of mapping it over again to something else. So we can go into the XYZ space, so we can do lots of transformations. It's a little tricky. I mean, it's a little complicated. It's too flexible in some regards. So it's an issue where you want to actually know what the difference between levels and labels are, which you want to specify. Strangely enough, the label is the third argument. You should, and it's got a default value. You shouldn't be specifying it. You really should be specifying the levels. That we tend to actually get the arguments in the order that they should be. They're more likely to be used. Okay. So that's one problem with this function, is it actually does the wrong thing by actually calling, by passing, by doing the wrong thing, by actually using labels instead of levels. It's not a function. Sorry, it's a. What else is wrong with this thing that you might improve? There's all this stuff. That's your thesis. Okay, that's your research. Okay, we can talk about that later on as to what you put in. But anything else here?
Use end row.
This end row. Okay, I didn't actually have to put this back in again because I'm just conditioned never to use this. Okay, that's bad news. If G is 0, it has dimension 0. This will be all sorts of bad news. I'll get an error because G square bracket 1. This will be 1 through 0, so there'll be two iterations, and G of 1 here will give me an error, basically. So it'll be okay. Now, when am I ever? Now, this is not a bad thing to do. Okay, and this is one of the perils of writing R code. And it's just so totally different when you write C or Java code, where you can't go anywhere until it compiles, which means you have to finish the entire structural entity. You don't have to fill out all the code, but you actually have to have the entire skeleton in place. Whereas the way people develop our code, and it's the right way, is one line at a time. You put it into a file and you run one line, okay, and then you or you sit there at the terminal and you, at the prompt, and you actually issue the line, it works, and then you cut and paste it and put it into the file. And that's the beginning of your script. Then later on, you're going to turn that script into a function, okay? This is perfectly sensible when you are writing interactively, because you know what G is. G is fixed, okay? This is not sensible when somebody else is giving you G, and G could be empty, okay? So when you're writing a function, you have to be careful about the inputs. You have to test the inputs. But here that makes perfect sense, because this is a script. We're just going to source this in or cut and paste it in, and life is fine. And we know exactly what context we're in. But this is a bad thing to do. What else is bad? Or it's not bad. Again, there's no bad. There's nothing wrong with getting it to work. Okay, you're done. You've got other things to do. R is a means to an end. Okay, as any programming language is. You're focused on something else. So nothing's bad. If it takes 2 days to run and you're off on the weekend enjoying yourself, that's good use of the computer. Okay, it doesn't matter how slow it is. Okay. But what could we improve? We're using, this is a global variable. It's not a global variable, it's just right there. It's only 3 lines away. Okay, but this is a function. I defined a function. This is kind of fun. We've kind of defined a function inside a call to another function. Okay, that's kind of weird. Ta-da! Everything will work because of the rules we actually said, because of this. The function, the inner function that we gave no name, will actually have its environment will actually be the global environment. Okay? Because, well, why? That doesn't make any sense. Okay? Because it was defined inside a call to lapply. So maybe it'll be, so we should actually know what the environment of this function is. Okay. Oh, it wasn't. It was an argument here. So it was actually evaluated at the prompt, okay, and then passed down. So we'll actually have the global environment as its own environment, in which case it can see num-replicates and it can see the whole search path, and life is good. Okay, what about mu and settings? These are also global variables. So one thing I would like to do is I should actually pass in num-replicates, mu, and rate. Okay, I should pass them in as additional arguments to lapply to pass them into here, and then I make parameters for each of those. And I can type in mu and rate and num replicates. I can use exactly those names, and I can use them exactly down here, because here they're variables that are being passed in from the global environment. Here they're parameter names, and they will get matched, even though they're the same names. There's no circularity here because they're being used in different places to mean different things. Remember that? Remember the brain twister we had last day of C equals C parenthesis C equals C equals C? Okay. They were all different. Every single C was different. So again, this would be better, because now we're not using global variables. But who wants to just write the same thing out twice? Okay. So, but it's a good thing to do in general. What else? There's one other thing I don't like about this.
You've recommended before that we make initialize a data frame as big as we think the size.
Only if you're using a loop. That's only if you're using a loop where you're going, and within each iteration you're going to add to the data frame. Then we want to pre-allocate and then fill in the actual existing but empty, essentially, the uninitialized values within the space that we've carved out. The beauty of lapply is it immediately makes enough space and then just starts filling in the elements. Okay, so that's okay. We're not in that state, but always a good thing to do. But when you're using loops, for loops explicitly.
So here we're making the assumption that the G, I guess it's a script, so it's going to have 2 columns, and 1 and 2 are going to be what you want it to be. But I guess somebody could not give you.
When we write a function, now we're going to be in fun. Okay, now we might think about making this in function. It's actually very entertaining, because you can how general will we be? And once we go really super general, then we actually have to start thinking super generally too. Our function becomes quite. We may actually have to start using things like substitute on match.call to actually do stuff. And you'll see in R we do this a lot, okay, to be super general. But let's just stick with 2 conditions, okay, just because otherwise, 3, it doesn't really matter what happens as long as Well, there is a, sorry, you were about to say, maybe you, because, no, go, it's different?
It's different about maybe defining that function outside of
This function?
yeah, I mean this is
So this guy's, there's also a global variable.
so maybe create another function and copy them and just call the function instead of defining the function.
Oh, no, I like this. I want to just pass in sim here. I may pass this in as an extra argument, so it's more general, so somebody can tell me what function to run. I've hard coded the name sim in here, but I can easily, because everything's an object in R, I can easily have if I made this into a function, I could easily sort of say, oh, by the way, what function would you like me to call? And you tell me it's sim, but I'm just using it generically. So it'd just be like a fun argument in lapply. You tell me what function. One of the problems I don't like is this. I see, so and there's a really very good rule of thumb. If you repeat yourself, you shouldn't be. Okay? There's this thing called the dry principle. Do not repeat yourself. Okay? As I always say, let me say that again, because it's so important. Okay? But it's it really is. You're trying to minimize the repetition, not because it's tedious. It is. Okay? But because there's infinite scope for defining things differently in different places. I have them in order here. I have these names, and then I have the same names here. And what if I gave them different names? What I'm actually utilizing here is the names to actually go and subset in, which just seems. So the least I could do is I could just say, hey. What are we doing? We're putting in new and settings here. The least I could do is in expand.grid, I should take the names of new and the names of rate. And that will at least sort of remove all this guy. And now I'll just have the names. And if I turn around and say, so somebody comes along and says, I don't like the word low, I prefer it to be something else, we'd have to change it in two places. This is where a bug happens, where you change it in, or you just change it in both places and you have a typo because somebody calls you or whatever it is, and you just have LW and LOW, and now you get missing values all over the place, and it's like, where do they come from? So we might as well actually try to actually do that. Okay, we just changing this to be names of con 1 and names of con 2 will actually help life a lot. We throw these away and life is good. Okay. The other thing is, I probably do want to make this into a function, but I haven't really spoken about how to write functions and so forth. So we can think about this. We'll let me just check where we're going. But we might come back and actually make this into a function. And if you want to, you can sit down and actually make it so it can take any number of conditions. And then say you'll have to think a teeny bit harder. So start simply. Okay. So that illustrates a bunch of things. One of the things we didn't actually talk about for various reasons was even though this is wrong. Well, let's just take a look at ANS1. Okay. What are the names of this? This is the guy we got. Haven't actually added those guys in yet. Let's just stick to this. It'll be okay. We'll go with the small guy. What I basically said, we shove in these conditions, and now you can go back. When we get it all right, when we actually put the right levels on and so forth, and we line things up in order, we can go. Lattice will do this for us. What are we doing here? Let me just do the following. Okay, so somewhere. I don't know where this is coming. Okay, let me just do this. Okay, so if you don't know lattice, many of you will use ggplot. Okay, so ggplot uses a lot of stuff from concepts from lattice. The fonts on these are hilarious. So what are we actually doing here? We're sort of saying this is A and this is low. Okay, this is A and this is medium and this is A and this is high. So what we've actually done is what we do in statistics all the time. Okay, we work with big samples. We vectorize everything because what we're always doing is the same thing to every observation in a sample. Okay, we very rarely do different things except for when we actually split them into different subgroups, and it's very natural to split this into show me all the A's That's everything here. Show me all the B, and then show me all the B's, and let's see if there's a difference between the A's and the B's. Okay, or maybe show me all the A's and the lows, and then the A's and the mediums, the A's and the highs, and so forth. So we look at two categorical variables, and we actually break up across all combinations, just like how we generated this with expand.grid. We put them all back together again. Now we separate them all back again, and this is so. There's a nice syntax for this in Lattice, which is. Here's your formula again, y. This is your vertical axis. This is your horizontal axis. But we're conditioning on these two categorical variables. Okay? This is a very common thing that we use in R. So we're just conditioning on these variables. Life is good. What does this do? Hopefully exactly what you think it does, okay, in those panels. It actually first does the following. It takes my entire data set. It looks at condition 1 and condition 2, which are A and B and high, medium, low. And it splits everything into subgroups, okay? And then we do this all the time. It's the group by operator in SQL. It's every language that deals with data analysis does this. So it's a split, okay? And that's what we actually use. We split them, and we end up with a list of data frames, each with a different number of them, okay, of observations, because there may be different numbers in each possible combination of conditions, okay? So let's just do the MT cars data because it's very easy to understand because there's only 32 observations, okay? It's kind of set up in a weird way, but let's look at this. This is automatic transmission. This is a very poor representation. These should be true or false, not ones and zeros. It's a data frame, so there's no problem representing it as trues and falses and having other columns like this. Cylinder. Cylinder is an integer vector. Should that be a categorical? I mean, the difference between 6 cylinders and 8 cylinders is the same as the difference between 4 and 6 cylinders. So they are actually on the number scale. However, they actually kind of they are qualitative in some regards too, but that doesn't matter. But if I say something like the following, which is split MT cars, $MPG. So let's split the vector of miles per gallon based on MT cars and let's just do the AM for one, okay? I get two lists back, different numbers in each because there's different numbers of automatic transmissions and non-automatic transmissions. So all I've done is I've just split, and I get back, there's only two possible, I get back a list with as many elements as there are unique values in AM here, two values, 1 and 0. That this is my split, and now what we typically want to do is, okay, I've split them. Now I want to do something to each subgroup. Let's compute the mean or something like this. So what we often do is the following: we then do lapply of that guy with the median. Okay, and I get back this. I know what I'm doing because I know that the median is going to give me back a single numeric value, so I can do sapply because I know I want it to collapse. Okay, remember, if I don't know that median is going to do that, then it might give me back an empty vector or something. Sapply may over-collapse this and give me the wrong thing. So remember, sapply, lapply. This is very useful interactively. Be defensive when you're programming generally, when you don't know what the function is going to guarantee to give you back. But now we just see this. This thing here is incredibly common. Split into subgroups and compute something on the subgroup, either a plot or a table or some summary statistics or an entire fit, a model fit or something like that. That's great. We can go off and we can do this. It's so common that we do it in one go. And that's what t-apply does, okay? It's a group by operation. Here's what we're grouping by. Here's what we're grouping. And here's what we get back is exactly, if you ever have trouble understanding what this does, do it as a split followed by an sapply or an lapply, okay? So if you go back up to what we actually have, it's exactly the same. Well, let me just verify. It's exactly the same thing. Look, even the same numbers, okay? So if you go back and then this is what we actually had. These are the two things we got. So this is the miles per gallon for AM0, for AM1. We got what we wanted. And what we can actually do is the following, which is we can do a list and say MT cars, and let's do cylinder. Okay, and now I get back again. Now I get back. What am I actually getting back? It's like a table. And this is why it's t-apply for table apply. These are the levels of the cylinder. These are the unique values. These are the unique values of AM. So we get a two-way table, and we get back the miles per gallon, okay, for both of these guys, okay, for each possible combination. And if there is nothing in here for one possible combination, then we will still get an entry which will tell us that there's nothing there. Okay? This is very similar to the actual table command. Okay? Well, so that's the table command. So if I go back over here and do the following. Okay, hopefully we get exactly the same thing, 3843, 12.1. T-apply of this and just tell me how many observations are in each is the same thing as table. Okay, it's just but this is much more general because I can do anything over here, whereas table is shorter, but table is just doing counts. Okay, whereas this is what we're able to do. So now, suppose I want to fit a linear model to each of the subgroups. Then okay, and this time, so what I actually want is MT cars. I'm going to fit miles per gallon versus weight for each of these combinations. Okay, but just for simplicity's sake, just give me the whole data frame back. Okay, so what I want is take my 32 rows and break them up into sub data frames, depending on the combinations of cylinder and AM. Okay, so what is it? There's 6 different combinations. I should get 6 different subsets. Okay, so if I do this, and hey, for now I'll just test it. Okay, it doesn't cost me much, and it goes, oh crap. Okay, what's wrong? N row is fine. That's fine. Okay, it should be passing me in a data frame. Okay, so it's an error in T-apply, not in N row or anything like that. Again, my little machine just stops. I have it set up to say stop and let me look around. I can look around. Doesn't tell me much. T-apply really says the arguments must have the same length. Look, this is a list with 2 elements and they've got 32 rows in each. This is a list with 11 elements. That's not the same as 32, okay? So there's a mismatch here. So T-apply doesn't understand how to deal with this. So there is another function that does know how to do this, which is named by. So just like the group by operation, it's just by, okay? And it says by now, but this guy here can actually take a data frame or a matrix. And it then splits the rows corresponding to the combinations here. This is a vector, this is a vector, okay? It actually goes off and constructs another vector, which is the combination of each of these guys, and then looks at the unique values and then splits based on that. So you can think of this as actually getting pasted together in some way. Now we get 32 values, then we group by that brand new variable. But because there's 32 here and because there's 32 rows here, we know how to split the 32 rows here. It's the fact in the T-apply that empty cars is 11, has 11 elements, and it goes, oh, I don't know how to do that. I've never been told how to deal with data frames, okay? So by is our friend in this case. So the rule of thumb, if you don't want to understand, remember what the difference is. When T-apply fails, you use by. Okay, that's a good default sort of thing. Why? Because by works on data frames. If you look at the help page, that's what it says. It says, I work on matrices or data frames, okay? But if we do this now, okay, now what I actually get is I get a very different printout from what T-apply gave me, and I get the number of rows in each subgroup. And again, if I did a split, I could see this actually happening. Okay, if you want to confirm this, you can actually do a split of MT cars, which does understand data frames, and then I could actually look later on. So just to be precise, let's just check I'm actually not talking complete nonsense. Okay, so if we split of MT cars of this guy. Okay, let's call this E. Okay, what's the length of E? There should be hopefully 6 different combinations of those guys. What is the class of each of these guys? Their data frames. And what's the number of rows of these guys? They're the number of rows we actually get for each. This hopefully adds up to 32. Let's hope no row ever made it into 2 splits, okay? And that everyone made it into at least 1 split. It's guaranteed to do that. And now life is fine. So the by actually does handle data frames, 2-dimensional structures, and we just split by other things. This guy here is kind of fun, the by. Okay, the by, let's go back up and get our by. Okay, we typically just spew it out and take a look at it. Okay, so let's go over here and do something like this, which, well, we'll keep it simple as N row, okay? Let's call this E. So what is the class of E? bi. Okay, it's a bi. It's the product of a bi operation. What is the type of bi? Because now that'll tell me how it's built. Remember, this tells me how I can think of that guy. It's hello. It is because they're all the n rows are all integers. Okay, but hang on a second. Let's just print it out again. We've never seen integer vectors printed that way. Okay. Okay. So what's going on here? It says this is the level of cylinder. This is the level of AM, level of cylinder AM, and so forth. Okay. An integer vector that has dimensions is a matrix. No. No, it's bi. Remember, it's a bi. Okay, but we just tag these attributes on. Okay, and R understands this. These are the attributes I mentioned to you before about names, the class, the names, and the dimensions. These are those three are kind of really vital attributes that we throw on things that R fully understands, and dim names as well. But here we've thrown on a dim. We've thrown on the dim names. That's how we get back the level, the actual, the cylinder values and the AM automatic transmission values. We've also thrown in the call here so we can actually look up its provenance and how did you get this. We got the class added on here. We can always look at attributes here and hey, we'll add another one. Okay, attribute E of food equals 10 for why not? Okay, that's fine. It doesn't affect anything. We can throw anything onto it. This is still an integer vector, which means I can do nice things with it. Like I can say, so what's the sum of E? 32. It's an integer vector, but it's got more adornments or decorations on it that allow it to be, that we can do computations on those if we know they're there. We can check if they're there. But R knows that if it's got a dim, then it should be printed a particular way. And because it's got this dim, I can actually also do the following, which is E of 1, 3. Okay, that doesn't make sense because the dimension, okay, it's only 2 in the second. There's only two guys in the second dimension, but that makes perfect sense. Okay, because I've got these are the cylinders, and then these guys over here are the automatic transmission values. Okay, the dimensions. So we can actually go in and mess around with this thing. So these attributes. So the bi is useful to actually know and understand and look and see what you've got because it actually has rich representation, but. This is also an illustration about these attributes. So if you want to have, if you have a data frame and you want to give it more adornments so that it carries extra information, you're entitled to do that. You just tag it on, and any functions you write can go and look at them. You could also just put them in a list right beside it, but then now you're dealing with a list with two elements, the actual data frame and the extra information. So you can't hand that to anything that expects a data frame. But if you have a data frame and you tag stuff onto it, it still is a data frame. So it will behave exactly as such, and functions will not get confused by having to look inside. Yep.
Can you just re-say, so I understand how dimension 1 is the 1 going into that subset, but I don't quite get how 2 is mapping onto 8. 2 is not mapping onto 8. 2 is mapping onto let me do this. We've got an integer vector because we looked at the type of. And again, it's not absolutely imperative that you understand this. This is kind of the sort of the reasoning behind it, but also sort of just the slightly more advanced way of things. We've got it. I told you it's an integer vector. What's the length of this guy? What's the length of E? It's 6. There's only 6 elements. There's 6 different possible combinations of cylinder and automatic transmission. Okay, so let me just, if I print E, we all see what it is. There's no real, hasn't shown us the two-dimensional structure. Well, it has, but it's doing a lot of work for us. We have to do a lot of work to figure it out. But if I do something like the following, matrix of E, and I'll just type it in where I know it's 3 and 2. Okay, and that's fine. Now we get, so now when I do 1, 2, we get back, there's 8 in the cylinder equals 4, automatic transmission is yes. Okay, so that's what when I go over here and do E of 1, 2, would it make you happier if I did the following? If I said E of 4 and I put in 1 here. Okay, now these are actually the values for cylinder and AM. Okay, happy? Happier? In fact, I'd be even happier if we did the following.
I keep switching between different things. I would be happier if I did the following. Okay. Now I get trues and falses. The dim names are now, okay, so dim names of E are false and true. So now if I type in E of 4 for the cylinder and true for the for this guy, I'll get back my 8 again, because now I'm using names rather than just positions, which is a much richer thing. It's much more explanatory. Happy? Okay.
So actually this semi-object is kind of unknown.
In this case, it is. In other cases, it will be a vector, because if we only condition on one thing, so if we condition on one thing, we just basically get back a vector in an ordered single dimension. If we condition on 2 things, it will basically be a 2-dimensional, and otherwise it'll keep going. But remember, we could get back some really funky things. Okay, so technically it won't be an array. Okay, let's do this just for fun. Let's do the following, which is what I said we were going to do in the first place. Function of, here's my, let's call it D. This is my data frame. So let me just do LM, a linear model of MPG versus weight on D. Okay? Now, what is the type of E? It ain't an array. It's not a matrix. Because I have got, in each cell of this, I have got a linear model, and a linear model is a list. So it's a complicated operation. It certainly doesn't fit into a matrix of numeric values or logical values, okay? But it's still a 2-dimensional object. Okay, so what's the dimension of E? It's still 2, because it's still the same, it's still the same organization of the different combinations of cylinder and automatic transmission. Okay, so let's just take a look at the very first element in this. It's a list. Okay, what's that? That's a linear model. What's its class? LM. What's its type of this guy? What's its names? Okay, there we go. It's got all this stuff built into it, but we can still think of it as a 2-dimensional object, but it's not an array. So technically in R, it's not an array, it's a list, because the elements have to be complex objects which are not primitives, not the logical integer numeric character vectors. Okay, and if I print it, here we go. Okay, we actually sort of see, so here we're actually sort of saying, hey, look, if you actually group by cylinder and automatic transmission, you actually get a change in the relationship between the miles per gallon and weight. Okay, there's not very many observations here, but it actually changes. So clearly these subgroups are not the same. Okay, you do not necessarily want to put them all together in a single linear model. So we can use dummy variables and all that stuff, but you can actually sort of say, look, the groups are actually different. Okay, so then this is what we do all the time. At least this is what I tell people in statistics. As my advisor in statistics said, all we do in statistics is add and divide. Okay, that's it. And if you think about it, that is all we do. Okay, but we're very clever about what we add and what we divide by. And we divide them into groups, and we say those 2 groups look the same. Now we can put them back together again and have a bigger sample size. Those 2 groups are not the same. If we fit a model for the two of them together, it's kind of stupid. Okay, so we have to fit 2 different models, and then we divide and add together. Okay, in different ways. So this is what we actually get. Now, I'm going to take a break in a second, in a few minutes. Okay, but let me quickly introduce this thing. How on earth did R understand to print this way? This is an object of class by, but it's a list. How did R choose to print it this way? And this is a good way of printing it, because if I condition on multiple things, if I have 4 different things in my group by, essentially, I can't represent it as a matrix, so let's just represent it in the generic way. Okay, so we just tell you what the levels are for the different things. So what would I actually, how does R know to print this? I'll ask you a different question, same question, okay? But, so here, what's the plot of R norm? Okay, well, let me just do this. Par and F row equals C of 2, 2, okay? And what's plot of R norm 10? What's plot of sample, we'll make it a factor of sample of A, B, 10, replace equals true. And what's plot of MT cars? I'm going to do. Okay, so here is one plot. Here's the last one I drew. Okay. And here's the first two I drew. Plot, plot, plot. How did R know to draw three different plot types? This is a scatter plot of my, Y is my random normals against the numbers 1 through 10. Okay, this is a bar chart of my factor. And this over here is the draftsman's plot of all possible combinations of pairwise scatter plots. How does R know to do this? And the answer is not that the plot function is the world's longest function. Okay? You're going to say the plot is the world's longest function?
I figure it has something to do with it's figuring out what the class of the object is, and then based off that, it has some method that it executes for that class.
So that's what, so you will come across this, and I'm telling you this because you actually have to know how to navigate these things if you're going to use them, but you can also write these yourself. I'll show you how to write one because they take 10 seconds to actually do. Okay, to get into this mechanism, and you decide what it's going to do. All of these guys have a class. The class of this guy is a numeric vector. Okay, the class of this is a factor, and the class of this is a data frame. Okay, so if we go and take a look, and then probably the first question I asked you is how did this guy know to print? Okay, how did this guy know how to print essentially a list, or when we were looking at the integers, when we just got the n rows, it was looking at an integer vector. Okay, and it says, I'm going to treat you totally different from the way I've ever treated any other integer vector. Well, R is basically doing this. So let's take a look at the word, let's look at the definition of plot. And it's this magic thing. And these are things called S3 classes. They come in order. S3, then S4. Okay, then there's R6, and then there's R5 classes. Let's totally ignore R5 and R6. They're totally different. Okay, and S3 is a very nice, simple mechanism, which allows us this polymorphic response. Okay, basically, plot is the generic thing I do, but the way it behaves is specific to the class of object I hand it. Okay, so basically we're saying same verb, different outcome, but all you need to worry about is the verb. But sometimes it's very useful to know what's going on. So when I fit a linear model and then I say, give me the coefficients, it knows how to do this. When I fit a support vector machine, the coefficients will mean something else. When I say coefficients of a classification tree, it goes, I don't think so. That doesn't make any sense. Okay, when I say predict this against this, okay, here's a linear model and I want you to predict new values, it knows what to do because it's trained, or it's coded to understand where to go out and pull the coefficients. For a classification tree, when I say predict, it knows to run it down the tree, each observation down the tree in a very different way, but you remember the word predict, and the software hides all the different aspects based on the class of fitted model that you're actually using. Okay? So it's the same thing, plot, predict, coefficients, you name it, all over the place. We're actually doing the same. We're doing different things with the same generic verb. If you wanted to make a new function called Bob, okay, you could say Bob is a function that takes some parameters. Oh, and by the way, it doesn't do anything except for go and find methods. And this is the use method of Bob here, okay? Or in this case, it's plot. Plot says, I don't do anything except for search for the right method based on the class of the first argument and only the first argument. And if you want to know the difference between S3 and S4, that's it. Okay, S4 can say, oh, you've given me a matrix and a logical vector, and the third argument is a data frame. I'm going to do something totally different based on the third argument, because if you'd just given me a matrix and a logical vector, I would have done something else. So it's smart enough to work off of combinations of classes. S3 is really brain dead. It says, first guy in tells me who I'm going to go to. Okay, and what does this do? And this is the world's simplest mechanism. I happen to know what it does for a data frame. Okay, Well, it doesn't, okay, but that's how I would find it, okay? Okay, here's what it does. And if we do, let's just see, print.by. Okay, there's the print.by. That's how it knew how to print or to show the by object, the E that I had earlier on. Because it doesn't just print an integer vector, it prints a by, and now it goes through and does all this stuff. So what's the mechanism? Plot, let's just stick with plot or print. Just pick your generic term here. Okay, plot, print, okay? It says use method. And here's what use method does. Okay, it is so simple. Okay? And you can actually do it yourself by hand to check. Okay? What does it do? This is the equivalent R code. Okay? So it's plot. Okay, it takes X. So what does it, this use method says, what's the class of X? Okay, and let's tag on the word default. Okay, I'm going to make a new vector here. Okay, so this is going to be, in my case, what do we actually have? We had data.frame. Okay, was 1, and default. The other one was numeric. And default, okay? So when we have these 3 different calls to plot, let's take the first one. It says data.frame, because we saw that was the class of a data frame, was data.frame. Not the type of, the class, remember, this is very important. So it says class of data.frame and default. Okay, I have a new vector with length 2, okay? What I do is I take my, I'm in plot, so what we do is we say plot, and we put a period in between them. We say plot.dataframe, plot.default. So we just paste this, we can create a new vector. And now, like the search path, we go through them one at a time. Is there a function named plot.dataframe? No. Okay. Is there a function called plot.default? Yes. That's the one I'm using. Okay. Down here, is there a function plot.factor? Yes, I'm using that one. And I call that and I'm done. Okay, it's the world's simplest scheme. It's just basically we take the class name and we append, or we prepend the name of the generic function with a period, and then go look for that on the search path. Okay, and that's it. Which basically says, so let's just do the following. Okay, so what was it? If I remember correctly, E1 is a linear model. So let's do this. Let's plot E1. Okay, there we go. It says it's happy. It says let's draw the first one. So let's go over here and, okay, that's fine. And then we go here. That's the first plot. Not a very exciting plot for a linear model, but nevertheless. Okay, here's another one. Okay, and it goes through the panel by panel. Okay, and we see these. Okay, so when it's basically gone off. Okay, it's drawn these different diagnostic plots for my linear model, which is totally different from drawing a matrix. But hang on a second, the linear model is a list with all this crap in it. Okay, so it says, no, the way you should look at a linear model is defined this way. Okay, as a sequence of 4 plots. Okay, that's just somebody's choice. It's not God-given, but that's fine. And as I say, if you do the following, so let's do the following. So let's do the function x equals 1, but let's just set the class equal to Duncan. Okay, and now let's say plot of Duncan, plot.Duncan equals the function that takes x and y and ... exactly the same as the generic function. And what's it going to do? Let's just play with it. We're not going to plot anything. We're just going to actually print something. Okay, we're just going to print hi. Okay, yeah, just print hi. Okay, let's put in. Okay, and now when I plot x, that is my function. That's how easy it is to define an S3 method. Okay, I created a class out of thin air. Okay, I just said you're a number. Now you're not. Okay, your type of is still numeric, but your class is Duncan. And now when I say plot, okay, it says let's look for plot.Duncan. I found it. I'm using that. I'm done. But if I don't have this, so now let me do the following, which is print of x, and it goes. There you go. I don't have a print.Duncan, so I'm going to use the default, okay? And if you take a look at print.default, That is that there is a default function, so it finds that. Okay, and the plot.default basically goes off and tries to make the best of a bad situation and then tries to draw something. Okay, so we can put this. Why is this useful? Good question. Okay, it's actually a lot of the modeling, a huge amount of modeling code in R is based on S3. Okay, it's amazing that we can go so far on such a sort of fragile system, but one of the really nice things is if you come along and sort of say, hey, I've got this really nice new thing. So we had linear models, and then we went to generalized linear models, then we went to generalized linear mixed effects models, GLMs, and so forth. If we have to go back and change plot, the one plot function to know about every possible thing in the universe. So you guys go, oh, I've come up with a brand new thing, and you have to petition the R core people who are very, very nice group of people who always take any changes with the greatest of enthusiasm. Okay? That'll be terrible because it will put all the burden on you to communicate with us, to add in more functionality that we then have to maintain. And all of a sudden, when two people, we both have the same name for a totally different concept, but we now would have to handle that. Whereas this way, everyone else can extend the system in a very clean, organized manner without the code getting longer. We're separating out the code. The code for my class Duncan is totally separate from the original print and plot functions. Okay, and it can live in its own little package, and we can do good things. And as a result, this is a very extensible mechanism. It's used in lots and lots of languages, any object-oriented system. And the point is that other people can extend this without actually being in a centralized place. And that this really is how hard it is. Okay, you didn't have to implement a print method, but you could if you wanted for the class Duncan. But you only have to implement the methods that you want to override. Let's take a break. Come back in 10 minutes, and then we talk about a few more things. These are not random number generators. These are pseudo-random number generators. They are entirely deterministic. You start at a fixed point. As long as we say start at the same point, make the same distance jump, I will be able to go and reproduce this over and over again. Just give me the same inputs and I will do something. There are these actually truly random number generation techniques. Okay, sometimes we don't want them. Sometimes we actually need reproducibility. It's not good to actually have that. But basically, that's what's happening. So when you set the seed, you are setting where we start from. So the next time around, we will start there. Setting that seed says, the next time anyone wants a random number, okay, they will come and ask for a uniform random number using this technique, and they will start again. So when you set the seed, the next call will start here again. So if I say set.seed to be some wacky number, 1, okay, I will start here. And then if I say R uniform, and I say X equals this of 1, and then Y equals R exponential of 1 and 1, okay, I get 2 numbers. Okay, I'm not setting the seed each time. I'm setting the seed at the beginning. So it'll jump to the first, for X, it'll be here, and now it'll be here. And now if I do any other computations, it'll continue on this way around. But if I go back and set the seed to be 1 again, okay, I will start back up here and get the same random numbers that go into this. I won't get this, if I reverse the order, I will get different numbers, but I will still get exactly the same deterministic thing. So I can set the seed anytime I want, but it only applies from now until I reset the seed or until I quit and start all over again. Does that answer your question?
Yes. And does that mean that you will get the same answer as I will on different machines?
Mostly. I mean, there are portability concerns and all that sort of stuff. The other thing we actually also have to agree on, that we agree on the same random number generator. Okay, there's a choice of 9 or 10 random number generators. So we need to say, here's the inputs and here's the algorithm I want you to use, combine them. Not very many people choose a different random number generator. I haven't seen it very often. So we will typically get the same answers, okay? But only if we do exactly the same computations, okay? And this is different. If I do this and this, and I write a loop, do this in a loop or even a null apply, see? That's different from R uniform of n and R exponential of n, okay? I'm still producing, if I do this in a loop, n times, the order in which I'm doing them is different. Here I'm generating n uniforms now and n exponentials now, as opposed to here I'm actually generating one at a time, so they're getting interleaved, and I will get totally different answers. So the same algorithm, but it looks the same, but slightly different implementation will give me different answers because I'm doing things in different orders. Okay, happy. But setting the seed is very useful. So, you know, if you're doing simulations, set the seed. Okay, just get in the habit of doing that. Somebody else had a question. That was it. Okay. Okay. So there's so many more things we could talk about as I went through. We did talk about S3. Okay, so you can actually define your own S3 classes. As I say, there's this concept of a generic function. If you're not defining that, if you're just providing methods for plot or print or anything else, you don't need to know anything about the use method, but you can define your own generic functions, the verbs yourself. The next method, don't worry about it. Okay, it's a way of doing fancy stuff. Let's quickly talk about writing functions. Okay, and this here I just tried to throw some of this together. Writing functions is really quite simple. We've already done it, and I didn't have to explain it, and at least nobody asked me about it. You know, I sort of, in the lapply, I sort of said, oh, here's a function that takes I as an argument, and we just use it, and hopefully it's reasonably clear. I mean, the simplest function takes no arguments, so the function is a keyword in R. It has to be immediately followed by parentheses, okay, white space, but other than that, it's, you know, function of one. You know, function space one is a disaster, okay? Function paren, if it takes no parameters, that's fine, okay? It can do whatever it wants. It can call R norm. It can call, you know, with one, it can just return a constant, no big deal. Notice that it has no return value, okay? In almost all languages, you need a return. That's getting relaxed these days. And basically, but there is something very important about that is it is always, the result of a function call is always the value of the last expression that was evaluated. Okay, and I'm gonna make that even more general. Okay, which, and again, these are just, to me, these are just useful rules because it just, but you can quite happily live without them. The value of the, so remember, we actually, when we started parsing, when we went back to the REPL, the read eval print loop, we actually sort of said, when you parse this, you can end up with an expression where this is x equals 1, y is equal to 2, x plus y, and you've curly braces, and you'll see that the body of most functions, okay, has a curly brace first and then a collection of expressions in it. And so we often see this as the body of a function. We also see curly brace as and then closing curly in if statements. We also see curly braces in while statements and for loops, okay? While and for loops. Curly brace is actually an R object, okay? I told you, everything's an R object, okay? Absolutely everything. This is the beauty of the language. You could just go, oh, look, there's a curly brace. Let me grab it. It's a list. Great. I can mess around with it. But the key thing is, so I said that the return value of this function, if this is the body of the function, is x plus y. But if this is an if statement, okay, if this is an if statement, if some condition is true, do this, okay, what's the return value? Well, I don't care, I didn't assign it to anything. But if I said y is equal to this, you better tell me what the return, what is y going to get? Well, the same rule applies. It's the value of the curly brace, which is the value of the last expression that was evaluated. That's this guy here. And if there's an else statement here, okay, well, let's get rid of this, okay? If the else statement is just 2, then what happens? The if statement evaluates this and then goes to here and evaluates this because the condition is true. What's the return value? It's x plus y. If the condition is false, it goes to here. It evaluates this, and that is the last expression that was evaluated in the if statement, so y is 2, okay? This is a nice generality. The result of evaluating curly brace is the value of the last expression. So I put an if statement in here. So if x plus y is less than 10 or less than 0, okay? If it's less than 0, then take the absolute value of x plus y. Otherwise, take the log of x plus y, okay? Then what happens? This condition is true, so we're in this block. So we evaluate this, then we evaluate this. Now we're in an if statement. This is true, then this is the last expression that was evaluated. Not quite. This is evaluated, that's the return value of if. And there are no expressions after this, so the result is the absolute value of x plus y. If this condition is false, then we evaluate this. The return value of this if statement is this. That's the return value is now sitting there. R looks around, says there's no more expressions. That's my value, and that gets assigned to y. Yep.
So if you don't have an expression after the if statement, then that expression in the if statement is the last thing that we evaluate.
So if we have if some condition, okay, and then curly brace, that's it. Okay, so we have 2, okay. Now, so then the answer is, if this condition is true, the result is 2, and the return of my function is 2.
Right,
so what happens? Well, I can't have if and nothing else.
Okay.
No, you can't have an if.
You can't have an empty.
Okay, so you know, if this. Now you have to have an if. This will parse. This will actually be a parsing error. Okay, if has to have something. But what is interesting is this: and we can try it. You can just try this. Okay, I have a function. Let's just write a little function that takes no arguments, and you know, if R uniform is less than 0.5, okay, tossing a coin. If it's less than 0.5, it's 2. What's the okay? So this is my function f. What is f most of the time? 2. Half the time it's 2. What's its value the rest of the time? No. Not nothing, because everything is an object, so it can't be nothing. Okay, so it's actually null, because the return value of if there's no else, is null. Okay, or if you didn't get to the missing else, it's null. Okay, so everything has a value. But the key thing is that actually it's the same logic. The result of evaluating the body of a function, or the body of an if statement, or the else statement, or while, or a loop, okay, is the value of the last expression. Okay.
So if you're wanting to work on a data frame within an if statement, and you want to say reassign some aspect of that data frame to a new value, in order to get back the whole data frame, you actually need to write the name of the data frame as the last statement, as opposed to just
oftentimes
because maybe your last statement was the reassignment just of specific elements.
It depends on where we're doing that. So let's just do this. So I mean, if you're doing something like the following, so you have let's just put it in a function. It doesn't really matter whether it's in a function or not. As I say, you want to think about it. But if I do something like this, if some condition is true, okay, then basically maybe I'll do something like the following. Okay, so let's put in here. This is my data frame. And if I put in this condition, then data frame of I equals, you know, and let's put in number 1, just making it up, is equal to 3. Okay, and then if I go on and then do something to the data frame, you know, summary of the data frame, then it doesn't matter. I don't have to return it, because I'm not interested. Here I'm interested in the side effect of changing df, and it's in the same scope. It's in this function. It can see df. This change is actually at the scope of the function, so no big deal. However, but there is this case, what you're getting at is, in many cases, we actually might, you know, we want to do something like the following, and this is important. You do something like this, if condition here, okay, and you say df of I of 1 equals 2, else df of I, and I'm going to change up the second column for some unknown reason, is equal to 10. Okay. Now, if I leave this like this, and then just return, and I expect the caller to get the update to the data frame, no, what they're getting back is the change to these elements. Okay, so they're basically getting back the value 10. Okay, not the upgrade to the data frame. So now what we want to do is we say, no matter what happens, always return the data frame. Okay, so that's what you're getting at, okay? Because here, if I leave it here, the result is the change to these guys. So essentially I'm getting back the left-hand side of this. It won't be just 10, it'll be actually the column, the full column, but actually just, it's a very messy operation. So you're nearly always doing that thing. But again, totally different from the case where we're not returning immediately. We're able to see the change inside and here. This is only when we're returning the modified version.
If you hadn't put df to return that, would it have made the changes to the df object?
Yes.
It just would return the 10.
It would most definitely would have made a change to the df object, but not the df object you're thinking.
It would have made a copy.
Yes, because remember, R is making a copy of this, and here it's writing it, so it has to make it. It definitely has to make a copy. So remember, the df object is my parameter. So when it gets passed in, it gets copied. When we modify the df, we're doing it inside the call frame of this function. we are not changing whatever the person gave to my function here. So if I want to see the change, that the function has to arrange to pass it back. It will not modify it in the space of the caller, which is suicide. Okay, if they do that, I mean, imagine you just call one of my functions that says, you know, all that nice data you have, I thought it'd be better if it looked like this. Okay, you know, your ones, I like two better. Okay, so you don't want anyone messing with that unless you decide, I will take your response and put it back and overwrite that object. So that's why there's you have to really figure out what do you mean by df, and it's the local guy in this function.
So if you want to see the GF, you change the function assign the server the function GF.
Yeah, I can choose any name I want. I mean, I might have. So you know, let's call this f. F is equal to this function. So if I go down here and if I say f of mt cars, and it's screwing around with my mt cars up here. Remember, it's a copy of mt cars. If I want to say now I would like, you know, I might say mt cars 2 equals that guy. So now I haven't messed with MT cars, okay? But if I want, I can quite happily say, no, you know, I'm done with it. I'm done with the original. This is now a better version of MT cars. I can quite happily assign it there. By the way, is that clear? By the way, what will have happened to MT cars if I do this? What will have happened to this MT cars?
That's not value, right? So you overwrote the value.
Original empty cars is in base, and so you made empty cars.
It's not in base, but it's close enough. Okay, it's on the search path. It's in the auto loads. Okay, so it's on the search path. So when I passed it in, I got a copy of it. When I signed it here at the prompt, it went into my global environment. So there's still another empty cars lying around. I won't see it because I'll find the one in the global environment first. But I've now got 2 empty cars on my search path. Okay, and that's fine. That's absolutely fine. There's no problem with that. But just be aware that the empty cars has not changed. The original empty cars has not changed. Okay? Happy?
But if you take the df out of that bottom function at the end, and then do that operation, you'll either have a 2 or a 10.
I'll have a column, 2s or 10s, yeah. Yeah, okay? So yeah, exactly. And it's, but that's totally different as opposed to, no. So, and by the way, you know, there's, what we talked about with S3 classes, you can actually have your own square bracket operator of Bob. Okay? Okay, or we call it Duncan. There was a class, we had a class called Duncan, so we can actually write our own square bracket operators. Okay? And we can also write, so you just write this as a function, and we actually saw that what the definition of the function was dot, and drop equals true. Okay, and then you're entitled to go off and send email to people in the middle of this function to ask for their answers, call a friend or something like that. You know, you can do whatever you want, and as long as you come back with an answer, that's fine. Okay, so that's how you subset. And you can, instead of treating it as an ordered collection, you can say no, they're all on the disk somewhere. They're all in a database. We can hide a lot of stuff. But you can also write a function that looks like this. Okay. And now this is the one that actually assigns. This is where you say x square bracket I comma j, or, you know, this guy equals, and this guy will get called for a Duncan object with this value. So you can do whatever you want. And why do I mention this? Because a very common mistake is I make the change and then I just return, which is the change. But no, you have to return X or else you're screwed. You've now completely wiped the whole thing clear. Okay, so this is very common. But this is how powerful you can change how assignments to sub-elements are done through S3 methods. Okay? So happy? What we're basically saying is writing functions. Okay? We can just actually turn, the return value is the last expression evaluated, and you can always figure that out. If it's an if statement, it's either null if there's no else, or else it's the value of the last expression inside the if, the body of the if, or the body of the else. That's great. We can have these anonymous functions. There's no reason why you want to actually save something to a variable name and then call it, and that's just throwaway. We write these guys all the time. Okay, here, this is a very common thing where we do them in lapplies. By the way, is there another way to write that function? I want to be ultra lazy. all of a sudden I can't type, but I'm happy to spend my time thinking. Okay, so every keystroke is really, really annoying. And I was about to show this when we did the lapply and the LM, the fitting the linear model on each of the subgroups. Can I rewrite this to avoid the function? The reason I wrote this function is because I'm passing in each element of doc texts. And so we have a vector, there's a whole lot of elements in it. lapply loops over each element and passes it to my function as the one and only argument. But okay, it's the first argument, and I want to call grep, but that object has to be the second argument in grep. So how do I get rid of the function? This is a quiz based on the first day, Tuesday of last week.
Just write grep and then comma, the name of the argument.
So we just need to find the actual name of the argument, grep. So it takes pattern, and then it takes x. Okay, and the fact that it's called x is probably let's do this. Let's do this. If I sort of say let's call this L, and loop over each element. Loop over each element. Now I call it element. So it's getting L is my name in my function for the thing the first input. It's just L. There's no other arguments. Okay, and then that's fine. Again, when I'm writing a function, I get to decide what the parameter names are. And other people can do it by position, or they can match my names, but I have to write the rest of the code in relation to, I need something to be able to refer to the parameters, so I get to choose, because I'm the author. Okay, so that is absolutely fine, but this is equivalent to, I don't have X, or I don't have doc text, so I can't run this. This is the same thing as writing grep, okay, with pattern equals foo, okay, because now grep gets called with two arguments. The first argument is L, the element of doc text. The second argument is a named argument called pattern. So what do? We match the named arguments first, which is pattern, and it actually happens to match the pattern first, okay? And then we do the partial names, and then we do the remaining ones. This has matched the first guy. So when we now get the unnamed argument, which is the element of here, the first available slot is the second argument, the second parameter of grep. So this is another way of actually writing the same thing. Okay? Okay. So that's fine. We can do all sorts of things. So you can do all this stuff. Okay, so let's, here's a function. Okay? This is a function. Let me tell you what we're doing here. We have a bunch of XML files, okay? If you don't know what XML is, don't worry about it. They came from PDF files. PDF gets transferred into XML because PDFs are really annoying to read. Okay, we now have a description of all the pages in an XML file. We have a directory of 2,600 of these things, thanks to some of these people here. Okay, so what I do is I basically say, give me a list of all of the XML files, okay? Okay, it's recursive. We don't do recursion here. We just say they're all in this XML directory. They're actually in subdirectory, so I'm probably going to need to do something else. Then I loop over and say, okay, give me, for each of these files, okay, and I say, give me the full name, so I have the full path to each of these files. I call XML parse, and we talked about some of this may fail, so I want to put a try catch in here or a try in here, but let's not worry about that for the moment. And then after that, I want to go through and I want to call, if you don't know anything about XML, don't worry about it. All this is the beauty of this is you no longer need to know whether these are PDF or XML files. It's just going to tell you the number of pages in each document, and that's what functions are for. Is I don't want to type these three things. I don't want to remember how to compute the number of pages. In this case, it's just get me the document, go find every node in here called page and count the number, okay? And then that's the number of pages and we're out of here. And if somebody else comes along and says, you know, I've got a much faster way of doing this, I can do it straight off the PDF and you don't have to convert them to XML, okay? We would hide this, we would change our function and you would still call get num pages. What is less desirable about this? What's less desirable about this function? How would you like to enhance it? When you start writing functions, you want to start dumb. Okay, write functions, make them do what you want to do and nothing else. And then hopefully what you do is a week later or 2 months later, you go, oh, I got to write this function. You go, God, it sure seems like I've written this before. And then you really should spend the time, go back, find that function, and then enhance it. while making a copy of it. Okay, to make sure that you don't break it for the other project that you're still working on. Okay, and this is where version control is absolutely vital. But then, many times what you do is you can say, I can generalize this function. How can we generalize this function to make it work? Like I just told you that what happens if I could do it straight off the PDF documents? I could probably do it straight off the PDF because I want to do something so simple, which is getting the number of pages. Okay, so I'm only getting a very small section of it, so I could actually read probably the first 700 bytes of the PDF document, get it, and say I'm done. And if I'm a library like where we are, and I have millions and millions of PDF documents, I may want to change this. So how would I generalize this? First of all, say how, what would you like it to do, and then we'll figure out how.
Different file types,
well, let's keep the XML. First of all, actually, I'm saying they're XML. XML is an extensible markup language. We can have lots of different extensions to indicate what they're for, like PMML, okay, the predictive modeling markup language. I may want that. That's different from an XML. I may have this as being XPDF as opposed to XML. So I probably want to change the extension on the files that I'm actually using. Pardon? So that's what we're going to do. This is very rigid. It takes no inputs. It's not parameterized. I do one thing and I do it very well. Okay, but don't ask me to. I can't do it. You can't even ask me to do anything different. Okay. So one of the things we might do is we might say, okay, let's allow it to take a different extension. It's also looking in one directory. You better be there. Okay, so a lot of what people do is they say set WD to go over to here, set the working directory, go over there, and come back again afterwards. Sometimes they forget. Okay, so and when you do that, you probably want to wrap that. Remember these on.exit function where you sort of say, look, I'm going to do a big jump over here, but when I get out of this function, I want to make sure to come back. So we use on.exit for that. So no matter what happens, if there's an error, we still always get back to the right place. This notion of if you set the working directory and then somebody else sets the working directory and somebody else sets the working directory, you have no idea where you are. Okay, so we'd like to make this a parameter. We'd like to make this a parameter. What else would we like to do? I was showing Matt this last week, and I take it to the extreme. Okay, my functions, I don't do this. I don't quite take it to the extremes. But my functions can almost always be written as a single expression in the body, and everything else gets done in the default values of arguments. Okay, because I like this flexibility. There are 2,600 of these documents. To actually parse this guy, 2,600 documents is very fast. So if it takes a second for each of them, it doesn't actually. Thank God, but it's 2,600 seconds. I don't have time for that nonsense. Okay. Secondly of all, I'm having difficulty with one of them. I'm trying to develop this function. It's great when you see it just works. Imagine it's doing something slightly more complicated. When you're developing this function, you don't want to run it on it. So it turns out that the one case that my function doesn't handle is the 2,600 document. So what do I do? Go through the first 2,599 documents and then wait till it falls over? No, I want it just to work on one document. So I need to be able to specify what the documents are. Okay, not just the extension, not just the directory, but I want to say, now, here's a smaller subset of documents to play with. Oh, and by the way, I've already parsed them, so please don't go and parse them again. So instead of actually passing in the file names, I'd actually like to pass in the docs. Okay, then I will go ahead and do my thing. Okay, so one way to write this, I think I've written it down, is to do this incrementally. And again, you do this incrementally. Don't go for the home run. Okay, and go, look, my function works. Now let me add parameters. Now it doesn't even parse. Okay, it's like great. So you incrementally build it up. It's great and it's wonderful if you're a software engineer with years and years of experience. You just write the code first time around. No, you don't. Okay, nobody does. Okay, but you have a fighting chance. But a lot of times you don't even know what you're trying to write, so you actually try to think about it. But when you're writing functions, okay, we're just going to put the parameters in here. Okay, so here I'm going to say there's the deer. So let's just compare the two. And again, there is an aspect of design to this and figuring out. So here's iteration one. Just let's lift the XML up here. So let's say here's a parameter called directory. The default value is XML. Let's take the pattern that we had down in here, and let's say the pattern is there. Okay. Now we just use dir and pattern. If the caller does not specify them, these values just go straight through. If they do, life is good. Unlike other languages, okay, the default arguments they don't change the order in which we call this. Okay, if we don't have to put the parameters with no default values first and then the ones with default values afterwards. No, they can just go in any order they want. It's very flexible. So why not put default values when they make sense? Now, the funky thing is these default values are literal values, but the bit that Matt was laughing at is sometimes I write functions where the default value of this is an expression, as an R language expression, that refers to other default values. And you go like, that can't work. But we've seen that it does. We actually looked at the computational model and sort of said, this is how it finds everything. These promises say that's no problem as long as they don't become circular, where I think I have an example here is where the default value of this guy depends on the default value of this guy, and the default value of this guy depends on the default value of this guy, and it goes like, hang on a second, nothing exists here. You're out to lunch here. But as long as one of them exists, this may actually be complete. So it may be that the caller doesn't have to provide a value for this or for this, but they do have to provide a value for one of them. That might be sufficient. But I mean, so this is kind of much more flexible, okay? But you can sort of see basically what we've done is that in this case, we had literal values in here, so it's very easy just to lift them up, okay? Put them up in here as default values and then just refer to the parameters. There's no point in saying dir equals XML and then putting the XML in here in quotes and going, you can specify the directory and I'm going to ignore you. That's even more frustrating. It says it's good, it's paying attention to my directory. Okay, so the next thing I actually want to do is I actually want to be able to say, look, you could actually give me the parsed documents. So again, one of the things we can do is this. Actually, I think I tell a lie. Sorry, let's do this step first. Okay, I did actually write it for a reason in this way. So why don't I explain it in this way? Okay, let me put the ... in here. Okay, doesn't cost me anything. You can specify the directory, or you can specify the pattern. But you know what? I'm going to let you specify anything else too that list.files will take, like ignoring the case or like recursive equals true. There's a whole load of commands. Okay, so what we could do if we wanted is if we take a look at list.files, it takes all these extra arguments. Path, that's the one. Pattern, okay, we've covered those too. But do you want all the files or just the hidden one, not exclude the hidden ones? Do you want the full names or not? We didn't specify that. Oh, we did, thank goodness. Okay, recursive or not? This won't work for my case because the XML files are underneath, in subdirectories underneath the XML, so I really should have said recursive equals true. But if somebody wants to turn that off, what do I do? Okay, I have to make, what I can do is I can copy every single parameter here into my function here, and same for XML parse. I can just copy everything in, and now people can specify them. So now my function has 12 million parameters. Okay, nobody has a clue what they do. Okay, I have to document them. This is really annoying, but this is much better. I just say ... and what I do is I say you can pass me any of these that list.files understands, and I will pass them straight on. It's your responsibility to get them right. So if you pass me down something stupid that list.files doesn't understand, the list.files will complain. But if list.files, if the people who develop R change list.files to have a new parameter that goes really, really fast, equals true or false, okay, or get the right answer, you'll just inherit that. Everyone will be able to pass it down. You won't have to change your code to actually do this. So that's kind of nice. Somebody had a question. Thank you.
So if you're passing parameter for list.files up in debug,
yeah.
The list.files know that it's going to take that.
It doesn't take it. Oh my God, no, it doesn't take it. Nothing. These functions never reach up. They can, but and I mentioned this by sys.calls and stuff. I said they can be very nefarious and actually see what's going on above them and do really stupid things. Nobody does that. These guys. So remember what happens. You weren't here, so okay. So this is what happens. Okay, and this is again. I want to. This is not just related to your question. I want to remind people when get num pages is called, what do? We open a call frame. We create variables, local variables in the call frame for each of the parameters. Then we go through this process of matching the actual arguments in the call based on the full name matching of the named arguments, partial name matching, okay, and then filling in the rest in the order that they arrive. Now we have a call frame. We're ready to go. And what does R do next? It says, okay, we've finished all that step. Now it looks at the body of this code, the curly brace, and it looks at this stuff, and it evaluates the first argument, or the first element of this expression, which is this line. This goes off and has to find list.files, okay? So it looks along. Now remember, this guy, I'm going to define this in my, I'm going to define this in my, at the prompt. Okay, if it was in a package, we'll get there in a moment. Okay, if this was, okay, this is defined with the environment of this function will be the global environment, and hence its parent environment will be the first element of the search path and so forth. So it'll look for list.files, find it, create a call frame for it, do exactly the same thing, matching all the arguments, and then execute its code. We don't care about that. Okay, take that as read. Now it's finished list.files. We've got the return value for list.files, and now it says there's an assignment. So now, which this is, I don't believe we've actually mentioned this yet. So, okay, so what do we actually have? We have a call frame. This is the call frame for get num pages. Okay, and we have dir equals this guy, and what else was the other guy? Pattern. Okay. Okay, so that's fine. And then now what's about to happen is ff here, okay? ff is about to become a variable. This is not a parameter, it's a local variable, but the call frame will hold ff, and that's fine, okay? So this is what happens. Now when we go along and we look for ff in the next command here, we're gonna look for lapply, we're gonna look in the call frame, it's not in there. Then we're gonna look in the parent of the call frame, which is the global environment. Keeps looking, finds it in base. Now it has to do these arguments. So now it looks for ff. Okay, where's ff? There it is. It's in the call frame. So we're good to go. That was an easy one. XML parse, not in the call frame. Let's start looking. This had better be on the search path. If this is not actually, if you haven't loaded the XML package, this is going to fail. Okay, but that's fine. That's another matter. Okay, but now. Okay, so that's the way the evaluation goes. So we start with the call frame, we fill in the parameters. These got promises all over them and stuff like that, but they've been evaluated. But now we also add in the local variables. Okay, everything comes here, and then we look around here and we look along the functions search path. Now, what about the ... Okay, so going back to our thing. Well, so somebody called this with. The actual call to this was get num pages, and I was totally happy with everything else. So we actually said recursive equals true, and whatever else. Let's do ignore.case, okay? And now we'll do .ignore, that's enough for me, thank you very much, equals true. Okay, so ignore.case was false, I needed it to be true. So what does this call do in let's go back to the argument matching. Okay, this is the argument matching. So we look at all named arguments here. There's only two, okay? Does this match the parameter name dir? No. Does this match the parameter name pattern? No. Okay, you got one last chance. Is ... in the pattern is in the signature? Is it a parameter name? Yes, it is. Thank God. Okay, then this guy gets put in there. Okay, we do ignore.case. So it's just IGN. Does this match dir directly? Exactly? No. Pattern? No. Partial name matching? No. Okay. Is ... in here? Yes. So this guy goes in here as well. Okay. So ... is now a list with two elements with names in this case, recursive and IGN. Okay. And then so now when we refer to ... well, it's sitting right in our call frame. So when R looks for it, it finds it in the call frame and it puts it in, it actually replaces it with, and this is where R has to be, it's a list, but it's ... It's incredibly special. Okay, so now it unravels those and it actually adds in recursive equals true, comma, IGN equals false, or true in this case, okay? Okay, that's all it does. It doesn't expand it doesn't expand IGN to ignore.case, but it basically inserts, it substitutes them directly in there, element by element, rather than as a list with two elements. So when R goes to do this, list.files, it sees IGN equals true, and it starts doing all the same matching from the parameters in list.files, and that does actually match ignore.case by partial matching, and now life is fine. So list.files never has to look up to see what's in ... It is given the actual arguments exactly as if you type them in there.
So if in the second line, the dot is LFI, there was also a ... and would it go?
Yeah. You'd like a ... for XML part and a ... for list.files. But if I put ... in here, I'm going to get that back ignore.case for XML parse, and now we got a problem. Because we basically got, so the ... cannot be a catch-all for everything, because otherwise you're going to have arguments that do not correspond to parameters in there. That said, any one of these guys, if they want, and this is where it becomes ugly, any one of these guys can say, I'm taking ... And instead of it actually matching, so let me try to say this quickly. Let me just do this, okay? If I do something like this, here's a function, ... okay? So here's, here it takes x and y and ... I am perfectly entitled in my function to do the following, list of ... okay? And here are my extra arguments. And now I can say if ignore.case is in here, then I'll go and extract the value, okay? I can go in and sort of say extra of ignore.case. Let's put it this way so I can type as case, okay? And I can sort of say ignore.case equals this way. It's a very ugly way of doing this, but I can go in and I can selectively pick out the guys I want and have things make sense. Okay, so what you'll see, like a very common example of using the ... is, oh my God, there's so many arguments to plot. Okay, like xlab, ylab, main. There's no way you can keep up with all these things. So I'll take them all down. Somebody has to look inside and actually check which ones are meaningful. Okay, and you can do this if you want. But at the same time, if you take ... you can also see that we do sort of things like the following, which is, if I put down ignore, okay, equals false. If I do that, I will then pick up the ignore down there. It'll match to this one, and I don't have to do anything special. But then I can pick up the ... as well. So a lot of what people do is, you'll pass them down, and then you'll add in the ... and just throw it all away, and let the person handing you the ... essentially expand the names. Okay. So this can be, what I'm trying to say is this can be used as I'll take anything, but I'm never going to look at it. So we don't even bother looking at it. But I'll add in all these other arguments that I do want to take a look at. Okay, and if you happen to hit any of those, but the real downside is if list.files wants ignore.case to be true or false, and the XML parse wants ignite, which has exactly the same thing, and we only use IGN to be a data frame or something like, oh my God, it's now getting matched to the wrong thing.
Basically, the ... top of the function is then it's going to get matched to your and first it's going to get matched to your list.file, and then when the LFI or XML parse is called, it's also going to get matched with that.
If we put this in here as this, if we put in, where was it down here? If we put in ... here, yeah, exactly the same thing. R never changes. It doesn't see we've already consumed ... It will say, no, I'll do exactly the same thing. I will fill in the extra 2 that we got element by element to make them look like real parameter argument calls and match them the same way. And if they match, great. And for the most part, this doesn't work out. This works out very well. Okay, we tend to sort of do what you're, but there's a trick to being able to sort of say, I'll selectively pick up some of these too. Okay, so that's fine. So this is already an improvement, okay, because now the bits about list.files, the user can figure out. Now they have to look and say, what can ... be? It can be list.files. It's the extra arguments to list.files. But it's kind of handy. So what's the next guy we actually do? This is the bit I want. I always do. I just lift this first line into the parameters. Why? Because remember I told you if I got 2,600 of these and the last one fails, Okay, well, I only want to tell it to look at the 2600th file. So I want to, instead of saying calculate all the files, now if this, if there's 200 million files, even calculating those might take a long time. So I may want to calculate it once and pass it in each time. But I may also want to be able to say, by the way, the file is named this. I'm not letting you calculate all the file names. I'm going to just give you the subset that I want. So here I just sort of say, if you don't give me the files, by the way, FF is a terrible name. Files would be a better name. But it was perfectly fine up here when it wasn't anybody's concern. Now it becomes a parameter. So now it's for public consumption. It's like, okay, maybe I should clean up my laundry here a little bit. Okay, but it doesn't matter. Okay, so now basically it says, if you don't specify it, I'm just going to do literally, I just take this line and stick it straight in. Okay, which is one of the reasons that Shay asked me, why do I use the equal sign rather than the less than minus? Laziness for the primary purpose. But if I had FF less than minus here, I couldn't make it a parameter by just moving it up, because that's an assignment. Now, this is beautiful. I don't even have to change my code. It's now a parameter. And I say, all these things bubble up. You can maybe guess. The next thing I'm going to do is move the docs up, because sometimes I've already parsed it. And then I'm going to have one line. Okay, and I could even say num pages equals the answer, and then just return the answer. But that seems a little bit gratuitously silly. Okay, okay. So the default values were fine, but notice that pattern is used over here. Okay, dir is used in here. Dot 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 is used. And it comes afterwards. Hang on a second. It was defined afterwards. Remember, nobody cares. This is all lazy evaluation. We're not trying to find dot 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 when we're trying to evaluate this first. Remember, these are all promises. So we have dir and pattern and ff now and dot 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 lying around. So these are all promises. The second anybody refers to them, well, it's just in any of this code. That's when we go find them. This is going to be a promise to this guy. We now refer to it. The first line here refers to ff. I need this, please. So it says, where's ff? It's here. So it tries to evaluate this call in the call frame, exactly the way we did it up here. But it needs to find pattern. Well, there it is. It's over there in the call frame, so no problem. And it's a literal value, so no big deal at all. Okay, and then off we go. Okay, and then what do we do? So this is the idea. And this is what, this is the way I work. Okay, I am not sitting, I want fast response. I tweak one line of code. I want a fast response. I need to go and check to see, does this work? And I say, oh, I'm going to sample 20 files. And if it works on that, well, yeah, it must work on all. Okay, maybe not. Okay, but or else I might actually say, these are the hard ones. Let's go chase these ones down all the time. I'll only check them all at the end when I actually believe this is working reasonably well. Okay, so this is great. And likewise, I'll say, you saw it coming. Okay, the docs goes up. Because now if I've already parsed these documents, there's no need for me to do it. Oh, even better still, and I do this. I did this morning. I parse the documents and I change them, and then I hand them in. I actually modify them to see, will this break? Okay, and there's no way. That means I'd actually have to put the file somewhere else, and I'd forget to pick it. I'll forget to remove it. And if I have no control over this, I'll put it back in the XML directory, and it's like, oh, that's a dummy file. 3 years later, I'll go, where did this file ever come from that has no pages or whatever it is? So this is very helpful for me to be able to actually specify documents and so forth. And now my function is really small. I've cheated. I put everything into the default values of the parameters, but it's now clear what's going on. People have a lot of flexibility in doing this stuff. This is an idiom I like to actually use. Okay, it's okay, and then sort of, as I say, we just parse the documents once. If I'm going to call this function 100 times, which it will, because it takes me 100 iterations to get the function right. Okay, when it may be a little bit more complicated than this. Okay, it takes me that long to do this. Okay, then I only parse them once, and I skip. Notice that when I specify docs equals this guy, I skip all these arguments. What is the value of dir and ff and pattern? Pardon? It's a promise that will never ever get evaluated because I never need them. Okay? I just skipped all that computation. Okay? These are sitting there. They will, if I ever reference them, they will take on their default values, but I will never actually bother to do that because I've specified I've specified the value for the parameter docs, and we never actually use this. Okay, we never use FF or pattern or anything like that, so no problem. It doesn't hurt anyone to have them default values, but we never actually use them, so life is absolutely fine, okay? And if you go in and debug this stuff, you may think it's being used, but only because you asked for it. Okay, you said, what's the value of that? It's like, oh, fine. You want to know? I'll do it, but I don't need it. R doesn't know you don't need it, just it thinks you're curious, okay? So this is one of the idioms I actually use, and it is actually a very important, a good one for actually making code more flexible for you and for other people too. Just constantly sort of looking at your functions and figuring it out. But one of the important things I wanted to get across while doing it, there's two things. One of them is this idiom of actually moving default value, moving code into the default values. Is also this idea of the call frame and that the local variables are here. We never talked about these local variables when we were talking about how functions were evaluated, how they work. But this is the missing piece. When you go in, when you go in and start evaluating this, the local variables, the local assignments go into the call frame, and then they get searched because we always look in the call frame. We look there first, and then we walk our way up through the call path, through the search path of the function. Okay. And that's really all there is to writing functions. I think this is fun. I like. Hang on a second. And most people, alarm should go, this can't work. Okay? One semi-required argument has no default value. Still doesn't mean it's required. I can check to see if it's missing. Okay, there's a function called missing that doesn't actually force it to be evaluated. File, and there's another argument y. Y is equal to the sum of non-empty. Okay, where's non-empty? When I look at this, I expect, oh, this is a global variable, but it's not. It's written here. Okay? No problem. I have never referenced y. Okay, so this will come in, it'll create a promise for files, it'll create a promise for y. Okay, it needs files, so now it immediately says, evaluate the promise. Goes ahead, you better have given it something meaningful. So it evaluates files, and then it loops over them and calls read lines, puts the answer back in LL, we get a local variable LL. Now it goes and loops over LL and gets the length, number of lines. Now we've checked to see which files that we just read have non-zero number of lines, which ones are not empty. Okay, and now we're going to do something with y. This will work because I've never mentioned y. I've never needed y, so the promise for y never got triggered. But when I put y down in here, now it'll be triggered. It will go and figure out what's non-empty. It'll look in the local call frame. It's sitting there right now. How did that happen? It's magic. It wasn't there at the beginning, but now it is. Lazy evaluation is what's getting us the result here, okay? It's a little cryptic. I do use this occasionally because now you should say, what's the default value? Let me just check. The default value is some variable I don't know. I have to read the code to find out what it does. Well, that's fine. You just hope that it actually makes sense. But it still allows me to set y, which can be sometimes very, very useful. Okay? So this is an example of circularity. The default value of y is the default value of x, and that won't work. So you will actually get beaten up for that. Okay. The return value, it's fine. Life is good. And this is an example of the if-else. So this time, okay, it hits the if statement. This is going to be the value if it's true. This is going to be the value if it's false. And this is going to be something slightly odd. If I call this function, and it runs through here, I will get the value from here, but it will not be printed. If I don't assign the value and I expect it to see it on the screen, it will not be printed because the last expression is an assignment, which suppresses printing. It's the equivalent of putting an invisible around here, which says, this is going to be too big. I don't think you want to see it. Okay? Whereas if we hit this guy, it's not an assignment, so we will actually, the result will print. So it can be very odd when something prints, something doesn't print, but that's absolutely fine. So this is the invisible stuff, okay? Fine. You will also see this, okay? There's no need for it at all. All you need to do is say X. Okay, but sometimes lazy evaluation, that non-empty case where y is equal to the sum of non-empty and it doesn't happen until later on, and it's so elegant and clever and cryptic and completely blows people's minds away. It's very annoying. Okay, but there are times when that's very useful. There are other times when you actually say, look, I want to evaluate y right now and I do not want to wait for lazy evaluation. There's sometimes very important. So there's a function called force that does the same thing as just y. If you just mention y, it'll trigger the evaluation. But if I wrote down this x and then y and then a big block of code, one of you would come along and say, why does he need this? Let's remove this. Okay, and that would be very bad news. Okay, because we need to force it. Okay, so this can be very useful to actually say force. Okay. And in the notes here, by the way, this is this mechanism. You can quite happily, as I said, you can be very nefarious and walk your way back up and see who called you and how, and who called them and how, and you could piece it all together and figure out what the heck's going on. So in theory, you could look back up for calls and then change the labels on your X and Y axis for a plot to actually refer to the real thing. That's about the only time you should ever do that. The rest of the time, you should not know. You should not change how you react to being called in different ways. Otherwise, nobody can reason about this. As I mentioned before, this is your call stack. This leads me to, we'll just quickly talk in a moment. You sort of see this call stack. This is scatter.smooth, my canonical example that we've used so far. You sort of see this. It can be done in the other order, of course. The order is not important, but so whether it goes from top to bottom or bottom to top is not important. But you are actually able to see where you are and see what all the calls are and what call frames are, that you are actually there. As I mentioned before, and okay. One of the things is this. So for those of you, hopefully you've seen some of this. Many of you won't have necessarily seen them directly because you're in our studio, you can point and click. It's very useful to actually know what's going on underneath this. When you write functions, as we just talked about writing functions, it's a good idea to actually put in all your default values and use that idiom to be able to make them fully, allow the caller to specify lots of good things, but not require them to specify everything. It's really, really nice. Okay. But after that, and then we assume that the actual logic and the reasoning behind the call frames and where you search, that's all reasonably clear. That's great. The second you write your function, you should have a bug in it. Okay, it'll either fall over flat its face and give you an error, okay, or it won't and it'll give you the wrong answer. In which case now you're in real trouble and you've actually got to go in and figure out what is going through. I was reading this thing, so I was just reading two things. Just one is saying always use a debugger, and there was somebody had a blog post about last week saying never ever use a debugger. Okay, so pick one, okay, or maybe somewhere in between. Probably a little bit of sort of moderation seems like a good idea. You've got a free debugger. For some of these people we're talking about, well, you're in C code. Why would you actually have to? You're in a different environment. In R, it's all integrated, so it's easy to actually just say, I don't want to use a debugger. Oh, I'll just be in a debugger when I get an error. Okay, so you can just basically say, I want to. If you get an error, I want to debug. Okay, or maybe then there's several options. You can basically say, if I get an error later on, immediately afterward, I get the error, I'm going to look at the call stack using a function called traceback. So you get an error, you immediately call traceback. If you go on and do other commands before that, the traceback will disappear, just like the .last .value we talked about. The traceback doesn't get preserved. Okay? But there's another way which is more proactive, which is you can say, I want to debug this function. Every time it gets called, I want to stop at the beginning and walk my way through to see what's going on. There is another mechanism which says, I don't really want to stop every single time. I know it's going to get called 100 times before the interesting part, or more to the point, I actually don't know how many times it's going to get called, but I only want to stop if the argument is a data frame with this many rows. Okay, so that's one thing. And then we use trace for that. We say, trace this function with this condition. Okay, but there's another type which the debug says I want to stop every single time. The trace says, I want to be clever. Trace by itself just says trace this function, which means just show me every time it gets called. And it just prints out, I'm in here, I'm in here, I'm in here, I'm in here, and you can count how many times and you can see that it's there, whatever. But trace also says, by the way, trace this function, but with this condition. I think I actually have it in exam. I can't remember. Well, I was tracing the plus one. We'll get there in a second. Okay, we have 5 more minutes. Okay, but the point with what you see with if we go back over to here, one of the things that I do all the time, if we go back up to here, okay, this is, remember I told you we did this thing here, okay? I got an error here in the t apply because we should have been using the by function. And I said, you may not see this output somewhere. I need to get the full output. I seem to have cleared it off. Where are you? Normally I have no problem finding one of these guys, okay? So here we go. So we saw this earlier on. Basically, here's what's going on. We called lapply, this was our lapply thing, and we got then it called its function, this guy here, then we saw this guy, okay, then it called the replicate called sapply, which calls lapply and then tries to simplify. This replicate calls this what function? It actually creates its own function with this guy in it. Okay, so life is fine. Okay, so it gets there. And I got an error. As I say, most people will just see the error message. So what I do in my .r profile, which is a file that gets read in every time R starts, it's in your home directory, okay? I set this thing called options, error equals recover, or browser, or whatever you want. Options, error equals recover, okay? Let me just do this, okay? So I have to, okay, you should just say this, and you say, I do this you can do it anytime you want. And you can say options, error equals null, anytime you want to turn it off, okay? But anytime I got an error, I get the whole call stack. And if you go back to look and see what was happening over here, it sits there and says, what would you like to do? Which of these call frames would you like to visit? And I just say, I would like to jump into here, because that's clearly where the error is, because that must be where the error is. And the answer is no, it's never where the error is. It's nearly always a little bit further above, because this is what's happened afterwards. Again, lazy evaluation and so forth. But this idea of options error equals recover will always give you a stack trace, okay? And you can start messing around with it. If you don't like this, but you only want to optionally go into it, well, you just hit 0. But if you want to actually say, when there's an error, I will choose whether to do this, you can just use the traceback function, okay? And it'll just open up exactly the same call stack, and off you go. And I can just jump in here. So let's just go here and do this. Okay, so there we go. Okay. Wouldn't you know it, this actually works. What was the thing? Let's just remove sim. Okay, and now we get the error message. Okay, so I think we can all fix this bug because I just actually showed you how to create it. Okay, but if we go here, we can actually take a look. So let's actually take a look at this function. If I jump into number 6, there I am. Now, nobody wrote this function. So what's the body of this function? There it is, but we never put it into a function. So somebody else did this for us, but now we actually see the function. So let me come back out of here. Let me jump up to number 3. 3, okay. And let's take a look at let's look at all the variables here. There's expression, n, and so forth. So let's actually just take a look at, let's not look at n. Okay, that's a very bad one, because n is how you move on to the next line. So n, we have to figure out how to get n. We can do that in a second. There's my expression, and it says now I'm trying to print it, but I still can't find the function sim that is in there, because it's substituted the value of sim. So we can kind of look around here, and this is what on earth are you doing? Okay, that's interesting. Okay. Body. Okay, so poor ESS. Okay, so here we're actually able to see this contents of our function in here. And again, we can. This is the function we're actually trying to apply. We can take a look at this guy. We can see what I is. We're in the first iteration of the loop. Okay, and so forth. So we are able to go in and explore here. And if I wanted to, I could quite happily say I is equal to 2. Okay. And I is now 2. I can change things and see if this will work. Okay, so here we're reacting to an error. If I debug a function, there's no error yet, and I'm walking my way through, and I do exactly the same thing. It will stop like this and give me these. I can look inside the call frame, and I can inject new variables and so forth. There's an art to debugging which has been written about in different languages and all that sort of stuff. But the key thing is to actually know these tools. Okay, one of the things I was looking at was this. I just need to find this guy here. So there's a function called f, or there's a file called f. This is one of these XML files, for example. This is very annoying, okay? This is a fun one that we were doing. This is a simple problem, so trivial. What is the title of this article? The answer, if you actually take a look at the PDF, it is very conveniently stored in the metadata. So we don't have to look at the paper, but unfortunately it's the DOI, okay? The object identifier, the digital object identifier, which is useless to us. Okay, so that's, throw that away. So now we have to move on and try to find the thing. So we've been going through these 2,600 documents and more, okay? And trying to say, what's a rule? What's an algorithm for finding the title of a journal article? Oh God, and they're not even all journal articles. So it's kind of like, okay, so we need a lot of heuristics here. But to me, the first thing is, well, it's the one with the biggest font, i.e. the Journal of Clinical Virology. Okay, they happen to have identical font size. Okay, so we can actually differentiate between one's bold, oh no, they're both bold. Okay, so that's not going to actually help. So we wrote code to actually try to pull this out, you try to find it in different places and all that sort of stuff. The trouble is, there's one document, this one here, which we're just looking at. So if I say get doc title, string of this one, I could end up with a bunch of trouble now. Second game. Okay. Okay. Here's what I mean. Okay. So let me just quit out of here. I'm now in the debugger, kind of. Okay. In a version of the debugger. Let me just do this. Let me untrace get doc title. I think that's the guy who's being. Okay. And let me also do is title bad. Is title bad. I was playing with this morning, so that's why they were already being traced. So now we do this. There's something else I'm tracing. What am I tracing? Where am I? So I don't know what I'm tracing. So where am I? I think I know where I got to. So this is the call stack. So somewhere I am now actually tracing get doc title. Okay, I think I did not untrace that one. Okay, but this is what I want to do. Okay, basically get doc title string is saying get me the doc title and then paste all the values together. So this is fine. So I'm not interested, but I'm stopping in get doc title. Why? Because the answer I'm getting is wrong. It's not an error. Okay, that's my problem. This is one of those annoying cases where it gives me an answer. It's just a wrong answer. I wish it would fail to give me a good answer. I gave me an answer at all. So here's what I'm actually doing. I'm stopping right here. And if you actually take a look at this, like trace of, so where do we get here? There we go. Somewhere I must have traced this guy up. Okay, but basically now I can look at the body of this code, and now I can walk through line at a time and see what is it doing. Okay, it says no, life is good. Okay, I know what this code is doing. You'd actually have to look in RStudio. It'll show you the code as you're paging through it. We can do that here too if we want. I've got it set up. Here is the title. These are the ones with the biggest fonts, and I've got the title. It's clear the title is here, but I've also picked up the Journal of Virology. So now they're like, come on, you got the right title, okay? So now I step through next, N for next, and so forth. I capital Q for just get me the hell out of here. Give up on this computation, it's a waste of time, okay? So that's fine. C for continue on. I don't want to go through each line at a time, okay? So is this an Elsevier document? Elsevier has this extremely common title in here, 2 images here. Okay, if I can recognize that, then I know it's an Elsevier document, in which case I kind of know that we have the same. Okay, so yes, so I execute this command. So let me check what is Elsevier. Okay, it's true. Okay, so then it must. Okay, so now we're going to go. Okay, and now I'm also debugging is title bad. I didn't untrace it. Okay, notice this. This is an S3 method. Okay, this is one of those funky methods. I've written it so that it is title bad, knows how to work off of XML nodes or text or a matrix or a data frame, anything I decide to have. So I'm able to walk my way through here. And now we're into this is title bad of XML node set. Okay, bingo, off we go. We can see what's going on here. Okay, it goes through a lot of calculations. Okay, we're all almost ready. And okay, there's the text. It's now got said, I'm not interested in these nodes. They provide a lot more information. Now it's actually saying, is this title bad as a string? So it's actually going off. And for some unknown reason, so now we're just saying, yeah, it's got the word journal at the beginning. That's bad news. Whereas what I really need to do is I need to say, the first bit is bad. Let me throw that away. Oh, then I need to change the logic of the function up above, and it becomes very messy. But now I'm able to actually find out why it thinks this piece of text is bad. And therefore what it does is, through elaborate design, it goes off and actually says, okay, these weren't the titles, because sometimes the journal is huge. Okay, so I'll go on to the next biggest one, and then the next biggest one. So it moves on to here. It gives me back all the authors' names. So somehow I have to fix the logic. But this mechanism, by stepping through and actually finding out what's happening, because if I want to, I can go on. If I wanted to, I could say the following. Okay, so now it's failed. It says the title is bad, so it's about to go forward. What I could actually do is I could have changed the title and taken out the journal, and said, here are the 2 subnodes you want. Try this. So if I want to do this, which is title bad, what was it called? Whatever it was. Whatever. So we could actually run it again with these, with this, I think it's, if we just do txt of -1, okay? And then we get an answer. Okay, and we hopefully get an answer sometime soon. And now it says, no, it's not bad. So if I take that first guy out, I can actually test this right now. And now I can make a change to my function and run it again and see what actually happens. So this is, as I said before, I think I said it earlier in this things. If you don't think it's worthwhile learning to use the debugger in R, and you use R more than once every hour, okay, so if you use it at all, okay, just learn to use the debugger. Okay, why? Because if you don't, you're basically saying, I won't have any bugs in my code or any code that I use. Okay, and you will introduce bugs in other people's code by passing in garbage. Okay, and you need to be able to step through and say, what the heck is it doing? So the argument against using a debugger that this person was purporting was, just read the code. Okay, don't do that. Okay, what a waste of time. Okay, there are good ways of reading the code, but they were basically arguing that you can reason about that entire code base. Okay, the bigger it gets, then let's just ask his own code. It just becomes incomprehensible. So these really, unfortunately, they're rarely taught and rarely emphasized, but they are really powerful. This mechanism with the trace is much more powerful. So here, stepping through debug. Trace allows you to say, and I threw in some example that says, do this when this condition happens, okay? And it can actually be, so it's as if you're injecting code into somebody else's functions, including your own, okay? So but that if you modify their code, you own it, kind of, and it now sits in another package or something like that. Whereas trace allows you to actually insert into live code into other people's packages and actually get the same effect and be able to sort of say, stop under this condition, or tell me what's going on every single time. The other one last thing that which we won't have in the Git repository, if I remember correctly, there is a thing called PKG. Okay, I showed you this. I showed you on the board last Thursday. This is an R package. Okay, you take the description file and you change my name to be your name. Okay, and other things. The description of the title. That's all you have to do. Copy it. You change the namespace. You can actually just use export pattern and it put dot star, okay? I'm being a little bit better. I'm actually saying, I want the plot function from graphics, and I export the plot function. That seems odd. I import and export it. I have an S3 method, which I talked about today, about writing a function for plot for my class. I have a function called my class, which creates constructors, but you don't need that, okay? And then the actual code is here, okay? That's a package. That is a full-fledged package that you are not allowed to put on CRAN. And what's the only thing that's missing from CRAN? The documentation. Okay, you have to write the documentation for these 2 functions, and there's lots of ways to help you do that. But you can put this anywhere you want. You can put this on GitHub and install GitHub from DevTools will install this package for anyone that wants it. Okay, it's a regular R package, no problem. That is as simple as an R package is. Okay. Many of them have many files with lots of code, and then I have some C code and C++ code and data and vignettes, but you don't need that. But you do need the description file and the namespace file, okay? And then you probably want some code, and that's it. That is all there is to writing a package in R. The help pages, there's a function called prompt in R that you say, here's a function, generate the page, and then you fill it in. Okay, it's all documents. It's really boring. Okay, it's really boring. Okay, and you only write the documentation at the end, because there's no point in writing the documentation and then going, oh look, I've changed the entire function. Now let me write the documentation again. Okay, and there are tools like Doxygen or Oxygen 2, which help you in some ways, hinder you in other ways. Okay, but that can automate a great deal of this sort of stuff. But the point is, it's really easy to write a package. And one of the reasons for writing a package is, if you want any help, if you want me, which I do this way too often, if you say, I'm stuck, Duncan, okay, or to Matt or whoever it is, I'm stuck, or to the Davis R users group, here, I'm having a problem. And they go, yeah, can you help me? And we say, sure. Can you send me something to reproduce it? Yeah, well, I got these 12 R files lying around the place, and there's data sitting in my C: users me, okay, not users Duncan and stuff. Whereas you can put everything in the package and say, this is the command that I use, okay? All the data are in the package. It's fully self-contained. I can solve these things, you know, sometimes in days and sometimes in seconds, because I have a fully reconstructible example. But if I see something like, okay, even it's as simple as this, if it's not just me, if you want help from somebody, if I have to detach 5 files from an email, it ain't happening. Okay, it's just too much work. Okay, and then I have to figure out how to call it. And your code is now referring to C:/ and I don't have a C:, a drive. So it just makes it really easy, and people will help you. And it doesn't cost you much at all. And it's really easy then to move it from machine to machine to machine. Okay, so for other people to do, but also when you get access to another machine, which is very common when you actually prototype on your laptop and then you go, I need a bigger machine. I'm going to go to the Amazon cloud and buy myself a machine for half an hour and it'll all be done, whereas it'll take 2 weeks on my laptop. That's good, but it makes it very nice just to pop it in. Okay. Pamela, did you want to say anything?
Just to wrap up the course answers.
Yeah.
I gave the post course today. It should only take over 6 minutes. Please do it. This really helps us. First off, to just have what they need. So Duncan opening teaching for doing this. We want to teach our you and help them learn through all this. So please fill it out there. Also, if there's building and suggest future workshops. So if there's something you want to learn more about, or if you want to continue on in this vein and learn more about the skill set, that's really information for us to know. And some of you might be interested in becoming an affiliate. So next week, affiliates are if that's still the case, come talk to you and tell you a little bit more about our program, what we're trying to do, and the community that we're looking to build here at the DSI for the data science. And just for those of you who perhaps you will interest, so Duncan is the director here at DSI. I'm not the director here. But we're not academic unit, so we are a very special entity. And I'm just going to leave it there.
So my purpose of doing this was just to actually stimulate, so that this is all knowable. I threw a huge amount at you. Okay, that this is you know, I say it's our fundamentals, but advanced stuff. You know, it is advanced, and you don't need it. But the conversation doesn't have to end here. One of the things that we really would like to have, especially with the affiliates, but in general, we are a very unique group on campuses that we don't really have a home to anybody, but we have this big space here that we'd love people to come and hang out, because I think this is where you actually find out when you can come and listen, but then you want to come back and ask questions. We have office hours. I have office hours right now, apparently. Okay, but there's also just talking to each other and go like, why does this work and why does this not work? And I'm around, other people are around, but also each other's around. But as I say, I may well do this very workshop again, or subsets of it. We'd like to know. Some of you would actually benefit from doing it again. This stuff never gets old. Because it takes multiple iterations. But there's also a whole lot of other topics, other languages, other, you know, we need to know there are people who want to learn this sort of stuff, and at what level. And some of it's just some of it's just making you aware of it. But the big part is just actually being face to face and hearing more informally than formally. These are fine. Anyway, so please come and chat with us and email us our feedback. But there's also this nice big space where we also have this thing that we were just chatting about today, which is we call them these unseminars. It's these this idea of, I have a problem that I don't know how to solve. So I'm going to give a talk of 10, 15 minutes of, here's the problem. You guys may have a different perspective, or you guys may know skill sets that I don't know. These are the sort of things that we don't necessarily do in academia a lot, which we tend to actually present what we do know rather than the opposite. And yet we spend all our time doing researching things we don't know. So this is the sort of environment we want to build here, which is come and help each other because it's highly interdisciplinary. Okay, so help us make this possible if it's of interest to you. Okay, thank you very much all for your lot of time. Thank you. They're on the front of the website, right in the front of the website.